But I'm also.
Okay, so everybody grab a seat, get this thing going.
What you're doing?
Longer, you're ready to sell that. Hey, welcome everybody. This is Great Brothers Institute 444. My name is Jim Masonbury. I'm the program director of the AFRL Small Business Hub. My job is to help small businesses, guide them, get contracts for the Air Force, educate them, get them in front of subject matter experts like the presenters we have today, and all other matters of working with the and federal government. Just some quick notes. I just want to talk about a little bit. Restrooms are right down the first hallway. Okay, where you'll see the big pictures of people on the wall. That's where they're located. As far as the breaks, if we're running a little quickly, we might take a break in the middle. Don't see how we're doing as far as time wise. But feel free, it's open to go restroom, grab snacks. Snacks are right out here, water, coffee is behind us here. You need coffee. Don't think we're gonna need some exciting presentations. It's a lot of good information today. So I put together the presentation, they're moving away. The slides will be sent out to all the people here attending and virtually, so please do not ask me that. I'm sure I'll get 20 other questions though about sending the slides out. But if you guys are okay with sending the slides out, I'm sure they're okay. Okay. The next collider is going to be May 9th, and it's a facility clearance collider. So as a lot of you know, being a defense contractor, one of the things you have to do is eventually you have to do is get a facility clearance with your company. You want to start doing more classified work, so you gotta do that. So we got some experts at AFMC and some presenters, and they've done that presentation many times. It's really good player. So in this room here, all these mics you see in the ceiling are hot. So please keep your conversations clear. Don't talk. Because you can't, you even like DJ is sitting in the back there all by himself. Well, Kim's back there too. She's reading emails. So if they had a conversation, everybody virtually can. All right, so just want to let you know. That's mishaps before. So this is the first time I've ever announced this, but I figure this is a good audience to let know and possibly help me and WBI out. But in FY25, we have no funding for this facility. So we're reaching out to a lot of the Innovation League on base. And so we're going through LCMC, AFMC, AFRL, asking if AFRL TDs, see if they can bring up some money, get the big chunks there out of them. But my job, being the small business sub director, I'm reaching out to small businesses too, to have a new kind of a look and feel of this facility, and not only just being funded by the base, but also helping from small businesses that I help support. So there's various different sponsorships and partnership levels that I'll probably be sending you guys. We have a nice little flyer, so maybe you'll be getting an email from me. But obviously, you did sponsor, you get your logo up on the wall. prominent space, obviously different sizes, for level of sponsorship. And, so I'm not, I hate to ask, but it's a tough one. I even hate to even talk about this, but it's the way the budget's going and stuff. So, with the federal government, so, our Springfield Street location will be open still, but 444 might close if we don't have funding. So, just wanted to do that little announcement. If you have any questions about this topic, please just talk to me after, or we can talk over at David Beer Company. So after. So lastly, well next I'm just going to introduce Sue Bausch from University of Akron. She's going to be opening remarks.
Good afternoon. I'd like to start first by conveying my sincere thanks for everyone who is here to participate in this slider. I'm not going to spend a lot of time talking today because we're here to talk about the presentations that are here and the network and try to get some collaboration going. So the UA and YSU team that we have here today brings together research expertise in an array of material systems, including polymers, metals, and ceramics, all of which have a lot of potential for use and applications in harsh environments. Our teams have significant experience working with federal agencies, including the Department of Defense, as well as companies of all sizes and shapes. So we're interested in collaborations across a wide group of entities. So the projects we work on range anywhere from TRL 2 to TRL 5. So we get those projects up and off the ground and hand them over to businesses to take them to market. So like the polymer industry in general, all the folks here today have a keen interest in sustainability because that's where we're all going. And our goal for this slider is really to open new doors and make new connections so that we have broader research avenues, applications, and collaborations. In particular, to new applications and materials needed by AFRL, NASA, and all of the folks in this room. So, like I said, we're not here to listen to me. We're here to listen about new materials for harsh environments. And so I'm going to turn it over to the presenters.
Yes, sir. All right. Never know if I'm driving or you're not. How you gonna do it?
All right.
Very good.
Yep.
All right. So, a little bit, so thanks for having us. How many businesses? Okay, how many academia? Youngstown, Akron, anyone else? Besides UD or Iowa State?
Ohio State.
Iowa State, okay. Cool. No right staters?
Lorraine County
Okay. Cool. Tech Center?
Community College.
There you go. Okay, good. Okay. So, I'm Jimmy Lawrence. I'm the deputy PEO for the Rapid Sustainment Office. I have my co-work here, Brian Stitt over there. He'll give the second half briefing. So for what you guys don't know, or maybe you do, Rapid Sustainment Office is a collaborative partnership on part of the Air Force with UDRI as our tech partner. So we have a very close collaboration with. How's it going? What's up? So we collaborate very closely with UDRI, one of the top manufacturing materials experts in academia today. That's not to mean there's other ones out there. They just happen to be resident with us. And we actually are co-located in their facilities with them as we do sustainment focused technology transition. I'll get into the charts a little bit here, but this will be interesting for extreme environments. Depends on which you're talking about, right? All the different services have their different extreme environments. Are we talking aircraft? Are we using hypersonics and Inconel? Are we using like cold temperatures out when we're in, an island chain somewhere or something? So there's a lot of different applications. Everyone here for additive then? Cold sprays and additive repairs and additive manufacturing and everything. Okay. So I'm not an engineer, so don't expect a lot of technical. That's why I have Brian. But I am the program manager.
All right, so let's go to the next chart. I don't like to just, so if you have questions, raise a hand, I'll try and answer it if I have to take it. So, the same office, for those who don't know, kind of orient, we're at, Airport Security Health Command, the MAGCOM, or the Matrix Command Center here in Wright County, Ohio, big building right off the highway. So we have a number of different, systems and centers. So 6 centers, 7 if you count the museum, it's the 7th one where they all go. You can see we are in the Lifecycle Management Center, so also located here at right outside the gate. You can see the other ones, the sustainment centers are very closely partnered with installation mission support, very critical for how we do our infrastructure. When you bring the technology, we do a lot of work with AFRL. Everyone familiar with AFRL, the Air Force Research Lab? I'm sure most people are. So we do very closely with RX and the Imperial Manufacturing Directorate. And then we also do some work with the new system center out there at Kirkland Air Force Base. So next chart. Wait for it. Okay. So a little bit about us. So you can read the mission, vision, and purpose, but I've highlighted some key red words. Go down, beyond why we were stood up. So when the Rapid Sustainment Office, does everyone know the Rapid Capabilities Office, or RCO out of DC, when they were stood up? Familiar with it? You go after very, very fast, more advanced technologies. If you flip that around, the Rapid Sustainment Office was a brainchild by Dr. Roper and General Wells at the time, to also focus the same kind of area on the sustainment aspect, because you really can't generate a sortie if you don't have the sustainment down, the maintainers doing the work out there to generate the sortie. So exploiting technologies, I'm not really here to build TRL 1 up. That's what AFRL does on behalf of us and other activities. But we want to look at commercial tech or things that are in that TRL 5 to 7. I'm not going to say I'm mandated by guardrails. I can take 4, I can take 8. We've done 3 and 2 before, but we want to use things that are existing, and then kind of apply the military utility to it within our environments and see how it reacts, how it works. We have some different authorities than my other PEOs. So we have cyber authority. So I've been delegated cyber authority by thank you. So I do have that. We've been designated as the lab by AFRL, so we have that capability. But then I also have acquisition authority to do prototyping, other transaction authorities, and everything else under the gun. So it's been a really fun time. So we can do all that. So we're looking at solving problems, though. You can read the vision and everything. We're all about solving problems. I'm not trying to just find tech and then find a problem to solve. I know I have lots of problems, so how do I go out and find that appropriate technology, bring that into bear, and then go out and solve that problem for the warfighter and leave it behind, right? There's a lot of tech innovation. We have the cyber program, we have a lot of academia, we have a lot of different things going on right now, but we need to make sure those are sustainable capabilities to solve the problems of not just today, but also tomorrow. Because a lot of times we'll put something out there. I mean, traditional Air Force acquisition, right? We bring the technology 10 years later, and the threat was 10 years prior. So what we're doing is trying to look ahead and see where we get at, and really does that accelerate those deliveries. We've been pretty fast in some of our other tech focus areas of delivering technology, including additive, but a lot of other things, which I'll show you in the next chart. You can see we have 3 operating locations. So we're right here. And then we have 2 other advancing technology training centers, one here in the Dayton region, another one outside of Robbins Air Force Base in Georgia, about 65% of the size, but have some similar and different capabilities that we use across the training center and also our CMC brethren on there. Any questions here?
Hey, Jimmy, just a quick question. I know, what's it been for you to get that cyber authority? What has it done for you? Because I know it seems like it's been very transformational, because before AFWERX kind of had the funding. What has that done for you from an organization standpoint?
That's a good question. So the cyber authority allows us to go after a lot of capabilities that we would probably find in the sustainment area. So the cyber program has been fantastic to lower barriers for small businesses to get into doing work with the defense companies and the DoD. When you were able to but that cyber authority it was housed in AFWERX, rightfully so, that's where they set up the program, and that's a good chunk of the business. But as you kind of dissect out the authority and apply it where we go, we can actually look at the small businesses and maybe have a niche in what we're trying to address from a sustainment aspect, maybe versus an R&D or some other kind of capability. If I said artificial intelligence, machine learning, everyone knows what that is. I go, okay, so what technologies do I need for what gaps, right? I already have a toolkit. I don't need the same thing 5 times over. So I'm looking for very specific technologies that I can execute funds against to solve critical gaps in teams that we see as part of the sustainable community. So it's been powerful. I know there's super authority limitations of how phase 1, phase 2, you do tag buys, strap buys, and other things. But we've been able to scale some of the small businesses very well using that super authority. It just depends on what niche we're looking for, what capability you have. Is there another question somewhere?
Where does your demand signal come from?
Great question. Everyone's familiar with MATCOMs, right? Like Global Strike, their Combat Command, all of them, right? So as an enterprise-focused organization, we work with each MATCOM. Sometimes the sustainment center, because that's where a lot of our sustainment technology challenges are. We accelerate delivery to them, but also HAP A4. So we look for HAP A4 to kind of aggregate that demand signal at an enterprise level and see what can we do to solve more problems than just one with a single or multiple technology. So it's very complicated. If I was in fighters and advanced aircraft, I'd say ACT gives it my demand signal, right? But I actually work with ACT, AMC, AFSOC, SOCOM, all of that, and then other partners as well. So I kind of go horizontally, vertically across the span and kind of gather problems.
Okay. Next question, rapid.
Yep.
What does that mean? That's like beauty. Beauty's in the eye of the beholder.
I would say it's very subjective, right? But if I go for a traditional acquisition program, it sometimes takes 2 years to get our requirements right, maybe, and then maybe we'll go through a 5-year funding cycle. We'll plan 3 years in advance, hopefully get that right 5 years prior, and then someone else gets stuck with defending the budget without inflation, right? So rapid to us is how do we take that technology? You'll see in a future chart, which we won't go to yet, kind of how we do a tech pipeline development within the RSO, which is our version of what I call force blanket on DAU. Because when you go back to exploiting technology, what is commercially available, I can apply military utility to, and do like an operational assessment in the field and leaving the users to actually get feedback. So sometimes that's good for me, sometimes that's good for academia, sometimes that's good for the small business because they just want to know, hey, does this thing work in a relevant environment? Is there a demand? Or should we look for a different use case based on, you may have started with a technology, but we think we can pivot that technology to that problem over here. So we've done a lot about that, and then we kind of put it out to the users. I'll speak a little bit in a couple charts about a couple ways we do that. We partner with the operational command a lot, and we want the airmen using the technology and giving us the feedback. So if it breaks tomorrow, okay, that's cool. You need to know that. If it's great and they need more of it, we've had that demand signal. Good question. Next chart. So, hit the bill. I think it's got the bill. So tech focus areas, right? So usually if I'm a fighter program, I know my F-15 is this. If I'm a tanker program, I think KC-46, 135 with that. So when the RSO is, we're founded on a bunch of ability twos, I'll say, which are what are your biggest problems across the MATCOM, sustained community, A4s. And then what we did is we took those ability twos and we said, all right, how do we use technology to fill those gaps? And these are the 6 tech focus areas that I'm responsible for on behalf of the Air Force on the sustainment community. So artificial intelligence, machine learning, obviously there's a lot of technology companies out there, it's used all the time. We've actually been able to use that within condition-based maintenance plus. You can find that out there wherever you're looking. And we partnered with one of the industry experts on that to actually deploy AI and ML across the CBN Plus enterprise on weapon systems. So that's that piece of it. It's called PANDA, Predictive and Analytic Toolkit for the and Decision System Toolkit for the Air Force. It was designated as a system of record last year. So we've been able to actually scale, I'd say what started as a mid-sized business to a large business now at C3AI, our partner. Across the Air Force, we're continuing to do so with good results on that. That's really determined. That's how you take unscheduled maintenance, which costs billions of dollars a year in terms of scheduled maintenance, and you can do it in depot sort of phase, kind of do it wherever you need to, versus down in an aircraft. We're going to talk advanced manufacturing though, so I'm the center of excellence for the Air Force when it comes to additive manufacturing, in partnership with UDRI and other companies out there that we use. We are responsible for the material qualification, the machine qualification, the process qualification, and doing all that work up front. So if you remember back in the 50s and 60s, those with aerospace, we go qualify a block of titanium and the source and the vendor, and then we go put it on a subtractive method, and we kind of hog out a part and we go, okay, we know how to do this, right? When we use additive manufacturing, we're essentially building a new car. So now we're responsible for the same qualifications we did in the fifties and sixties, put on those aircraft in a different environment. So we're doing a lot of the upfront work right now. We're gonna talk about that. Brian's gonna hit that in more detail at the end of this briefing on how we do it and where you guys can help. Automation robotics, huge in the depot. So how do we use automation and robotics primarily to kind of take the airmen out of harm's way, chemicals, accelerate capability, be more repetitive in what we're doing if we're talking about sanding or painting and things of that nature. Augmented virtual reality, so extended reality. So from a training aspect, if you think about multi-capable airmen, we have all that for the Air Force right now. So how do we do telemanagement? How do we do, hey, I got the airman downrange, needs to phone back to a 7 series technician at a base somewhere back here. We're actually working those capabilities with our major command right now. How do we accelerate and bring that training capability to bear? Rapid and austere maintenance environments, very interesting, very applicable for the Indo-PACOM theater and other theaters like that. What do we do with structures and green powered energy and things of that nature to go out there on an island chain maybe where there's nothing, there's no infrastructure grid, and maybe we have to do 14 days of operations before we get it going. And then data and digital environments, you can take that as you want, but that's essentially how do we stitch everything together in a cloud-based form or using APIs or other nature? How do we accelerate that data transfer across the enterprise to make it more efficient and not have like 100 different systems that we have to go play? So the maintainer has to do this system and that system, and that system, and that system. It's very inefficient. So we're looking at how do we accelerate that capability. Any questions on the TFAs? Okay. Next. This is probably the chart you care about that. So when I talk about, the 5000 series of the JSIDs, you can go through, decades of development with your RDP capability, software, business system, all the different pathways. This is our ability. So our process is called identify, apply, scale. That's kind of how we approach technology and how we get into the user pretty quick. So you can see kind of along the top what we do, on the bottom the attributes that we look for. So instead of building this big data package for a small capability that may or may not transcend across the enterprise and scale, we do it incrementally as we find out it has more capability and more fidelity across the mission sets that we're looking at. So obviously operational needs. So you ask like, where's my demand signal come from? Sometimes it's the airman on the RMAX, sometimes it's MAGCOM, sometimes it's general officer. They come from all over the place, but we kind of look to see what would have the greatest impact across the enterprise for what technologies we want to invest in and try and provide that solution to the end user. So alignment is huge. That's to our vision. That goes back to the ability to, I'll say if it's anything like sustainment, yes, it checks my box. I can do it now. How do I apply it? You get back to the enterprise level. So what we want to do is look for those big impactful efforts, and they can be small efforts that have a huge impact across multiple stakeholders and users. I'll take customer advocacy is probably the biggest one. I mean, so you're probably seeing this from each of your respective polls right here. You want it to be a pull system. You don't want it to be a push system, right? Because if I keep pushing things and it just keeps hitting the wall and failing, we don't want that. We want it to be a pull where that customer is saying, I really need that technology. And we're able to go and then solidify that as part of our fabric of what we're going to do from a capability standpoint. The problem is defined and understood. I'm not saying that you 10,000 requirements in a JSIDS document right now. Just give me some attributes of what the problem is. That gives me a lot of decision space to go after and find different technologies and solutions. We can fill that gap. And then it says around TRL 5. I played left and right of that, but that's kind of where we want to be because when we talk about rapid, if I take a TRL concept of one, I'm not going to get that to the field in like 18 months, 12 months, right? That's going to be like a 3 or 4 development project. I'll do some of that. But at the same time, I'm looking for those things that are kind of mature, maybe haven't been to the field, maybe they've been tested at some level, or can I just go out and play with it and see if it fills the gap? So that's kind of where we start. You move left to right. We do some market research and solicitation. We've got about the SIBR authority. We can go out and use the AFRL process and open specific topics, pull from there. We can go out and do other market research that we're doing. We actually have a commercial solutions opening that's open from 25. Everyone knew what a commercial solutions opening is. If not, it's an ability to go out on SAM.gov. I can go out and put a problem statement out there, and commercial vendors can come and apply for that, and then issue the Part 12 commercial contract, and we can take that technology and use it in a new innovative way. That's kind of the summary of it. That authority, I think, was solidified about 2-3 years ago by SAP AQC as the PBARs. It became a formal tool, so we've had one of those and still have one out there. When you go left to right, we call these the splatterbug charts. So, you're never going to hit 100% of all your KPIs, right? I mean, you could, but at what cost? So when I started playing with this, I go, all right, so here, I only got 5 attributes that I'm looking at. when I'm in my apply. So can I take technology based on the operational need and can I apply it to a problem and how's it gonna work? You can see we still carry over the MVP criteria, fills the gap, strong customer advocacy and user pull, so we have some way to use it. Market research shows best of breed. So we are constantly doing market research for the best of breed because of the pace at which technology is transferring these days and moving around. If you were the best of breed yesterday and you haven't, overthought about what you're gonna do, maybe you're not the best of breed tomorrow. They use the Kodak solution, right? Who's got the camera? Kodak did the pivot and look what happened. You're on. So can I leave the product with the user? So that's where I like to go and say, if I go to, I don't know, Ellsworth Air Force Base and I want to try something, can I leave that with the airmen in a safe environment with calculated risk where it's not going to kill someone or hurt someone, that they can actually use that on a real activity and give me the feedback and see if it fits the need or I get rid of it to move on to something else. Acceptable technical and programmatic risks. That's how we kind of pair it together. So you look at that, we go through that and we say, all right, well, here's a minimum viable product. Or minimum production aspect. So then we get in there, we go right to left. So you're probably wondering what these pathways of scale are, because when we get over here, what we want to do is we want to look at how we're going to scale this, or is this product scalable across the enterprise? There's a lot that goes into that, but these are kind of the 11 criteria. I have the team actually looking at them again to make sure they're still relevant. If there's something we're missing based on 5-4 years history. So pathways to scale, what do we do? Summit Lighthouse, anyone even know what I'm talking about when I say that? All right, anyone familiar with McKinsey? All right, so McKinsey, if you look at their documentation, we actually leveraged a lot of the work they did when we set up the RSO to say Lighthouse is a concept essentially of how you can test capability. So we go through 2 different ways. When we have let's just call it a hardware solution for something, we can do it with software too, we do it all the time. Summit is essentially, if I take that one widget and I put it at Palm and Ellsworth and JBSA and Anchorage and Wright Pat, I'm now testing that same widget in multiple different environments and locations, right? So same technology dissipated across service. Lighthouse, I actually have a Lighthouse technology where I put everything together and integrate it and see how it works with all the other capabilities. So I have 2 different ways to test capability on where I go. I currently have one Lighthouse, Nellis Air Force Base. That's really where I have everything. We work with those partners out there to do an integrated type test, but then we also have Summit Technologies as well. So if I go back to structures, right, I have a number of different structures for different capabilities that are in need in solar powered activities. I can put those in Indo-PACOM, I can put them at Tinian, I can put them at Wright Pat, I can throw them out behind W, I can put them on the roof here, doesn't matter. I can see how they react to the different environments, how they draw power, are they doing what they're supposed to do, and can the user use that? So we've done that in multiple ways. We've deployed a lot of our technologies with the Mobility Guardian 23, Northern Edge, a lot of major exercise that you hear. And what we do is we assemble all this data, that's feedback, and we determine, should we now scale, right? Is this technology going to meet the majority of these requirements, and these 11 are the outer circle here? Because something's probably not perfect, right? Maybe it's huge in WLTF and performance, but maybe it falls short on SS&E planning. We figure that piece out. That's called risk. So then we bring that to the board of directors. So our board of directors right now is governed by 2 4-stars and 3 stars. So Honorable Hunter SAP-AQ is the chair. The co-chair is General Richardson, AFMC commander. Then the 3 advisors are currently the LCNC commander, Lieutenant General Shipton, the AFSC Sustainment Center commander, Lieutenant General Hawkins, and half A4 Lieutenant General Miller. So that goes back to where my command signals come from, kind of all over the place. But we have a very flat organization where the director of the topic, we need to get a decision made. That's how we kind of execute our technology development. Any questions on this here?
So do you have funding to take a project from, we'll just use Civil 1, Civil 2, get your prototype, everything works out fine, test fine, wherever the locations are, and kick it to production? Or do you require sponsorship from a particular SPO to go carry it that through? How do you transcend the valley of death?
Both.
Okay.
So I have SIPR funding and I have appropriate funding. I have 3,600, 3,400, 38. I can do all of it if I need to.
Okay.
Primarily though, if I use my SIPR funding on behalf of a stakeholder, let's call it the Sustainment Center with a robot, right? Because of the demo operations. I can take it as far, and I can actually go procure those with 38 funds and buy a subset of those as they kind of put it into their, capital improvement program and look for what they're gonna do. We call it the tech transition value, that's with funding. So how do I use transition funding? Because of our long, funding processes, I'll say. We would like to make sure something is successful when we go and scale it, or if there's a need where we can actually program 2 years of funding as they ramp that, as we ramp down and they ramp up, kind of go over that valley there. We do have everything that, because there's only a limited budget, so we look for the best of breed, but we have the ability to do so. Then we can solicit from other stakeholders or match comps, if it's something they really want. We can start laying in that budget in the palm now. We can start looking at what we have available and kind of work those details together. So we do have a way to transcend the value, which is kind of unique, right?
Very.
That's why.
Hey, Jimmy, I know you guys have had quite a few successes with the rapid sustainment office. Can you share any of those?
Yes, I gotta figure out which ones you want me to share. So I've had software and hardware. So let's just say software, right? So we've been working with a small business up in the Northeast, near the Hanscom Air Force Base area, where they've been able to provide a capability coming out of the SIPR program that's kind of grown into a piece of our lighthouse, which essentially what's the front sheet for the maintainer when you're trying to digitize all the documentation and planning for that. We've actually taken that pretty far. And we've actually got about 5 or 6 ATOs. Everyone familiar with the ATO process? Who's a software person in here? Yeah, it's a horrible process, no reciprocity, but that's really what kills the small businesses. When you have to go fund the ATO process, put all the controls in, what you tried to do, and didn't develop it that way. We've been very successful gaining ATOs for at least one company right now in the software world. We got about 4 others. And then we're working with some other major vendors too. We're not just small business, we have large companies as well. Getting those to scale, and we're kind of approaching, we've been here for a while. We're getting to this point because that has a huge lightning rod across the DoD budget cycle, obviously, if we're gonna make that enterprise program. When you talk about additive, you'll see about a little bit about this later. You've been able to qualify for the Altera and what are the two?
Altem and Antero.
Yeah, Altem and Antero, sorry, I went back about it. But then we also did aluminum alloy, so we got safe use determinations through those. So right now we can use those within 5 parameters on certain printers that we can produce out in the field and deliver. The polymers are the easy ones. I think everyone knows that in this room. The metal is a little harder, but we're also working on qualifying about another 6 to 7 metals, and they're in various stages. So we got another pre-qualification, which Brian will speak to later. On some of the other ones. Why did we do aluminum alloy? Because it was a little easier to test the process on the DoD side of how we qualify that, but it also has applicability to some of the stakeholders that we're working with. We have a number of other structures that have been used, that we've been able to scale. Some of the combat readiness teams, those organizations kind of go places, have asked us for certain capabilities, so we've been able to take some of the small businesses that produce those products. One of them being the SPIS, so solar power integrated structure. The button shows up in about 3 minutes. That started as a purse. The concept was a solar powered purse. So we actually worked with the company to kind of turn that into essentially a big old thing like this stage that pops up, and you can take it out to an austere environment, pop it up, and start powering your capability on the solar generator. So we've done some interesting things with technology that you may not think you're going to be there. So we take and go look at the gaps and say, we can probably take that, tweak it a little bit, and solve that problem right there, and then make it, we can stock list it with DLA, which is what we're doing, so everyone can get it, or we can put a page 3 super contract in place, with, a price supply and enable it with the council. So there's a couple different things that we've done across the different spectrum of technology.
So when you, sorry, when you have an operational need matched with a technology solution, are you still looking for other technology solutions if the match has already happened with a couple of them and you're supporting them?
Absolutely. Does the threat change every day?
Yeah.
Yeah. So just because we find one doesn't mean that the next company or something's going to happen. We always want to be, ahead of the facing threat, not behind. So just because we found one doesn't mean that gap is closed, because from an industrial base perspective, we'd rather not have a lot of sole source vendors that we have to rely on that can only produce 12 widgets a year. I'd rather have 100 different companies that have variations that are qualified to be. So we never stop. We're always looking. That's part of our charter. Next. Okay, so back to where we're at. Advanced manufacturing, so I told you I was a center of excellence, I think it's DAFI 63-149. Department of the Air Force Instruction, and 63-149 nominates Advanced Manufacturing Program Office as the center of excellence for the Air Force on additive manufacturing and other technologies. So I have this team, I'm responsible for that team. We have 4 lines of effort. You can see the technology assessment, so you'll see a lot of this in the upcoming slides Brian's going to give you. Where we look at the machines, the processes, materials, qualification aspects, use cases, things of that nature, very technical. Airworthiness certification support. So I think it's a lot more complicated in the Air Force than it is the other services, because when you put a plane in the air, you're putting an airman's life in danger. You need to make sure you have the right material properties and what you're doing. That goes into the qualification process. I think a lot of vendors, at least in the literature I read and the companies I talk to, are struggling with that qualification process. We can 3D print stuff all day, but when you go to airworthiness, you go through that qualification process, it's very arduous and requires a lot of testing. Whether it's crack growth or tensile strength or how you do it. But there's a lot of benefit to it, right? Because now I'm looking at parts these days I never thought I'd be changing. If I'm flying B-52 and changing something that's never even envisioned to be changed, how can I use additive to do that? But what happens if I put a more durable part in there? Does it change the failure modes and everything else that occurs somewhere else in the plane, and I have a different issue? Some of the things that we looked at. Product support. So how do we do these strategies for advanced manufacturing? How do we enable the technology to our users? How do the technologies there for the airmen? How do we staff the depots to get after it? We're a larger scale manufacturing and repair capability. Then how do we deploy this across the enterprise? So both additive manufacturing and additive repair, we have cold spray, we have directed energy disposition, we have a whole these different things. We're always looking for the next best use case of these. Obviously, additive is still an emerging technology within the DoD and still being characterized among industry too. But you're probably going to see a lot of things we're doing. You're like, oh yeah, we're doing that too. And ceramics is very interesting to me. I even saw coating in polymer, right? So if I put metal coatings over polymers, can I up the strength and can I reduce the cost as well and still get that durability that I need in certain aspects? You can see the priorities scaling it across the ALCs and the field locations. So ALCs are our 3 depots at Bill, Robbins, and Tinker. Those are primarily where we do our program depot maintenance, or how we bring the aircraft down, repair, and get it back in the air on a defined schedule. What can we do when something breaks and we need to go print something, right? Coordinate with stakeholders, evaluate opportunities to improve readiness, always out there looking for the next best thing, what we can qualify, what we can use. How do we budget for it, right? It's going to be critical because as we put new technologies in, how do we get the powder? How do we get the raw feedstock? How do we do all that? Where does it come from? Are we USA compliant? Are we very minimum compliant? There's a lot of restrictions on what we can do. So we're trying to work that with the Industrial Waste Council up at the Air Force level. And then how do we use TPA Type 3 through AFRL to kind of expand that capability. And then we're in a number of DoD-led working groups, sometimes leading those to kind of define the policy of the goes, apply how you build it, and see how that goes. So this is what the AMPO team is responsible for. And I think after this chart, click the next one. Yes, I think you get more technical. So before I let Brian come up here and talk about engineering and materials, because he's smarter on that stuff. Any questions for me on the RSO or the technical series or anything I went over? I'll be here for a little while, but then I gotta jump out for this for another meeting. So yes.
You had mentioned under SIBR, you also have TACPOD and StratPod. Do you actually award them, or is that through AFRL?
So I can actually award a TACPOD and StratPod. I work with AFRL, so I work with Colonel Lee very closely. I'm trying to use the process as much as possible, but I have the same authorities. I currently have a StratPod in my organization right now that we used to award a follow on to. So we have the same abilities to do it, but we follow the same, I'll say, regulations and rules from even DoD down. But I haven't defined authority that's separate from his.
Okay.
Yep.
So the word is RS, or the acronym RS, so rapid sustainment. How much of that is also about sustainment? So there might be technologies which, there might be succession issues with a, a $10 million per year type of business. So how do you view sustainment or sustainability of some technologies that might be supplier limited, and because the founder might be retiring and that technology? So how do you view that, and is that within your program?
A little bit. We work very closely with the sustainment center. So I'll say that the 448 supply chain management wing of parts, ELA if it's consumables. And then we're just working with Sustainment Center and we find out that something is going away. That's where reverse engineering, so we have the ability to reverse engineer and scan and actually do the TDPs, technical data packages to produce the part again, the qualification with those materials. That's kind of the benefit of additive is when those sources that were probably gone 20 years ago and now I need it. How do I find it? If I don't have the source material drawings, I have to go create it. But we actually do a lot of that work in conjunction with URI and other universities too. We have the REACT lab down in Oklahoma that works very closely with Rose State. We have, is it Mercer State down in Robbins, or is that Mercer Robbins and Beaver? So we work very closely academically, but then also within the DoD as well to kind of get after those. And that's where there's really opportunities as well. The small business, large business, and academia to help fill it out.
Thank you.
All right, Brian, you.
All right, we're gonna get into fun stuff now. All right, so I'm Brian Stitt. Hopefully everybody can hear okay in the back. Let me know if you can. I'll probably be moving around up here. I can't stay behind the podium. So, Brian Stitt, I'm with the University of Dayton Research Institute, and I'm the division head for sustainment technologies. So within our division, we have everything from coatings technologies and paint and depaint of aircraft and non-destructive inspection of aircraft and ground support equipment, through repair using additive manufacturing, cold sprays, HVAC, all types of other areas where we do the high velocity coatings. And then into the additive manufacturing and advanced manufacturing, which we'll talk about. And then we'll also get into the robot automation piece. So all of that starts to drive the sustainment side of the business. And so our partnership with the Rapid Sustainment Office allowed us to bring all those together in combination to go address the issues that are being seen out there. Okay. Now, before we jump into the slides here, I'm going to ask a few questions of the audience here, if I could. So I know we have a lot of people here, but I'm interested in, Jimmy asked the question originally, it's like, okay, who started additive manufacturing, advanced manufacturing, and so on. So just really a show of hands. So on the additive manufacturing side of things, where do we have individuals or businesses who are working in any of that space right now? Okay, all right. So can I ask you a question? What type of work do you do in the space?
I mostly test them. I don't make them, but
Okay.
we've done a lot of titanium and nickel-based super alloys.
Okay, excellent. We had a few in the back as well. So where do you guys play?
We're developing an AI-based design software where you put in the requirements and then it spits out the design that fits out.
Okay, excellent, excellent. Go back here.
Yeah, so we develop AI models, AI machine learning models to determine the quality of parts, additive manufacturing parts,
Okay.
and to make it more robust. So we are collaborating with UDRI for many of our project work. And currently we have a SITR phase 2. And also we have worked with NASA with the dual technology development in the same field actually. So we have a software platform which can detect many of the anomalies during additive manufacturing process, particularly metal additive manufacturing.
Okay,
Yeah.
all right. We have one more. I thought we had somebody over here. Yeah, out here.
Well, I actually worked with the PIU Ensign on-ramp hub,
Okay,
and we're working with any Ohio businesses, connecting them to Ohio resources, government problems. So we have a whole cadre of companies we're working with.
excellent. Let's do one more. Got back here as well then.
We are developing a solid state additive manufacturing process using sheet metal rather than powder.
Excellent. Okay, so you go from powder, you have wire bed, you have sheet metal, so all different aspects of the additive type process. Excellent, excellent. Okay, so when I ask the question and I say, what is the difference between additive manufacturing and advanced manufacturing? What are your thoughts? See a difference? I see a head shake. Yeah.
Well, I think maybe the advanced manufacturing tools from cybersecurity, like additive manufacturing, the microelectronics, it's just some bigger umbrella.
Bigger umbrella, right? Bigger umbrella of advanced manufacturing, and then additive starts to fall under there. And additive, so when we talk additive manufacturing, a lot of times people think one of two things. They'll think, okay, polymers and metals. So when I say that, does that resonate with people? It's like, okay, you see your kids, your grandkids, wherever it might be, and they're printing in school and they're printing in polymers. And then you talk to someone back here and they're like, yeah, we're printing in metals, right? additive is still a process, and it can be additive in metals or polymers. It can be printing of circuit boards, which then leverages polymers and then other type metals. But additive is a growth process. So being able to take a look at what the problems really are, and then finding the correct solution is where the key is. And where the industry as a whole, when you think about additive manufacturing, advanced manufacturing, a lot of times they'll develop this great technology, you can print metals. Well, then now you're trying to find the problems. Well, what can I use this for? There's not always a great fit for being able to say, hey, I'm going to use this additive solution to solve this problem. We really have to look at it from an industry standpoint. So what's the problem? And then put the appropriate solution in place. Maybe additive manufacturing, and maybe something that falls under the umbrella of advanced manufacturing. But it's really aligning that solution with the problem so we can progress it forward faster. We had a question about rapid, right? What does rapid mean? Well, there are a lot of lanes that we operate in. One might be, hey, we want to do a quick check and see if this is something viable. That's fast, it's rapid, we're able to do that. When we get into some of the things that we're going to talk here, the material side of things and how we can progress these technologies, it might take a little longer. But in reality, it's still rapid compared to industry progressing these technologies forward as well. So we want to look at this holistically and make sure that we're really putting the appropriate solutions in place using advanced manufacturing to really solve the problem. Okay, so any questions before we get started and get into all the fun stuff? All right, if I could have you click the slide, please.
Can I ask a quick question? I missed the question. I believe this is for Jim. When is a new technology introduced into the ALC depots? At what stage in technology pipeline?
So when is technology introduced into the depots?
Yeah.
I'd say at what risk level are they willing to take it?
Because depending on what it is, we can take it all the way to full testing and go and deploy it. We can give you a prototype solution that they can finish, or we can finish if they're happy with it or kill it. I think it depends on the technology, the gap you're trying to fill, and the criticality of that. So we have a number of like robotic things that are about to come to fruition and finalize their design. If those are successful, it's now on the depot to take those on. We transition them in, and then we help them kind of define what that life cycle plan is and what they're going to need for a procurement aspect if they need more of them. So it really depends on the technology. It's not one and done. We're here on milestone C and we go. It's kind of depending on the appropriate. If you remember my tech pipeline chart, it's the acceptable programmatic and technical risk. There's some things that are lower threat and there's some things that are higher threat. We want to make sure no one gets hurt.
Okay, thank you. Yep. Excellent. All right, we can go to the next slide. We're going to talk a little bit about how we go from the beginning to the end. And I'm going to start over here on your left, my right. We're going to talk about the house. So we're going to talk just as an example about additive manufacturing under the advanced umbrella. And how do we get from point A to point B to C all the way up to the full qualifications? Okay. The industry has been around for a while. So additive manufacturing, while we're really pushing this forward, it's made a lot of great progress. Additive has been around since the late 80s. Okay, so the first machine for purchase, they were the polymer side of things. We started to progress that technology. What I like to do is I like to take this and liken it to composites. Who's familiar with composites? Most everybody? Okay, so back in the 60s, 70s, when we were talking about composites, and all the aircraft manufacturers and everybody like, we are not putting what they would call rags and glue on our aircraft. It's not going to happen, right? Where are we today? Okay, we're flying fuselage that have, composites. We're flying fan cases on engines, front fan blades, the cases. A lot of composites that are happening now. It's because we're able to navigate these types of processes to build the confidence in order to take those to the next level and use them for the next generation. Okay. At this point, do we use polymers for structural? Not from a printed standpoint, but you can from a composite standpoint. So now what we have to do is progress these technologies through these process steps in order to build a confidence level so that everybody can use them appropriately to solve the problems they need. So over on the far left here is the powder specification. So powder manufacturers. Okay, when we talk about powder, we're talking about laser powder bed fusion, which is taking a powder, exposing it to a laser, and then the laser grows that part. Okay, it solidifies that part as it grows. Okay. Years ago, when we started looking at the powders, the industry says, yeah, we'll provide you all kinds of powders. Great.
and we're gonna provide them with our certification. Okay, that's great. Okay, we have certification, we got it, we're running. Okay, what happens when you have a certification versus a specification? Anybody have any ideas? So when they certify it, they can change it. They can say, hey, I'm gonna change the chemistry, or I'm gonna change something about that material. I'm still gonna certify it to you. I'm still gonna provide you a certain performance. It still meets what I'm telling you it meets. But we don't have a specification, so to speak, that we're buying into. Once you get a specification in place, now that has a binding contract that says you have to provide it to us per this spec so that it doesn't change. Okay, so if the chemistry starts to change, it's gonna print differently. If the shape of the powder starts to change, it's gonna print different. So we have to lock down those specifications holistically as an industry so that we can really understand what we're gonna get and reduce the risk and variation as we move forward through the process. And that's where we come to the risk side of things, and are we able to move it forward? So just looking at the powder side of things on the far left here, a lot goes into it. It's understanding the chemistry. Okay, so we're gonna run a Ti-6-4. Whoever's familiar, I mean, somebody mentioned titanium. They had familiarity with printing titanium. What's the chemistry of the titanium compared to what you would get in a rod? Is it exactly the same? Show of hands, do you think it would be exactly the same? No, it is a little different. Okay, so the chemistry is a little different. And so we have to be looking at that type of stuff, those types of specifications and background, so that we can really understand what's going to happen, so that we don't end up with corrosion or stress corrosion cracking or something else that's going to show up through the process because it is slightly different than what you would see in a rock product. Okay. Quality control goes without saying. I'm not going to dig too deep into quality control, but being able to manage that at the powder level, it's a big deal because we have to understand what's coming into our process to reduce the variation. Powder size, particle size. You don't think about that much. You got a big thing of powder and you're looking at it, you can shake it and say, that looks pretty good. But when you get down into the morphology level and you're really looking at the shape of those powder particles, it can make a big difference. So when they go through the atomization process, if they're nice and round particles, when I spread them and recoat them in the machine, it's going to be great. If those particles come out and they have a bunch of rough edges on them, and they look more like a meteor or a meteorite, they're going to tumble over each other and they're going to cause issues as we go through the recoating process. So we have to get all the way down into that level of powder qualification and certification in order for us to be able to progress forward into these next steps. So that's just the starting point. Understanding just the powder is the starting point. As we move over here to talk about material specifications, now we're getting into where we've taken the powder, we've exposed it to the laser, and we're getting into the testing. So as Jimmy mentioned, we got to go through all this validation side of things. We have to understand the material properties. That's where we're coming into here on the material side of things. Okay. Mechanics of it. Okay. Getting in and understanding the tensile properties. That's just like the price to play, right? Getting tensile properties. Is anybody familiar with doing material testing? We got a few. Okay. So if we want to go to what we would call a B basis or an A basis or something like that, we have to go through, let's just say 10 lots of material. We have to run hundreds of samples across multiple machines in order to build that database for the MMPDS data system. Okay, to help all that process. Okay. Powder. It's fairly new. Okay. We're starting to ramp up in the powder inventory side of things. But I could call a company and say, hey, I need to do 300 samples. I need 10 lots of data or 10 lots of powder. Okay. You know how long it might take us to get 10 lots of powder? They may only run a lot of powder once every 2 months. If I need 10 of those, it's just a simple multiplication, right? I can be 2 years by the time I get another 10 lots of material lined up. Okay. So it's all built into how we manage this, and how we can manage the growth of supply chains. So as we go through this process, it's great to get from one end to the other. But if I can't get enough powder down the road to ramp this up, that's even a bigger problem. Right? Because we put solutions in place to problems, and now I can't get the powder in order to go ramp it up and roll it out into an ALC or ramp it up out into the inorganic supply chain. So we have to be working hand in hand with each one of these industries as we move forward so that we can go and progress that. Okay. Now, if we get into the material side of things, this is where we're getting into microstructure. We're getting into heat treat operations. Everything's a little different, right? This is, you can't say it's one for one. Hey, this is rock tie. this is printed tie, we're gonna use the exact same things. They're different. And you have to design for your manufacturing process, whether it's additive or something else. And so this is the phase where we're creating the material specifications and the quality control behind it. So that when you get up into these phases for parts, engineers can now design for additive manufacturing. Okay, so for those of you who have played in additive manufacturing or any other space, here's one of the things. A leader comes to you and says, this part, I want it printed. Okay? And you look at the person, you say, okay, that's great, let's go get it printed. Why? Why am I printing it? Printing because they want to print it. Right? And you're going to do what your leader says, right? I need to print it. It might not be the right solution. So then your next question is, okay, I'd love to print it. Can I change the design? And no. It would have to be the same design. Right? So now things sustain that. You have all these old parts on aircraft, and somebody comes to you and says, I got this part, can you print it? The answer is typically it can be. Okay. But if the answer is no, we can't redesign for additive, kind of put yourself in a box. And if you get out to this point, you're putting yourself in a box. So we have to really understand the material specifications, getting into the process specifications, so that designers in the industry can design that manufacturing operation. Okay, we're not designing for a casting anymore. We're not designing for a subtractive part. We're now designing for additive. And we have to design appropriately for the manufacturing process. So that's why it's key to get through these steps so that we can actually go here and produce the parts. Okay. As we go through the material side of things, again, a lot of testing has to happen. So you have a lot of test samples. It could be fatigue, it could be tensile, it could be crack growth propagation, initiation, all the stuff that goes into it so that we understand as design engineers, how are we going to design for this hardware? How are we going to design for this process? The last piece of it before we get into the part side is the process qualification. Right? So now you have the process side of things. Okay, so you got the chemistry and everything going into it. Now you've got to get into things like, how am I going to go through operator training plans, build documentation, everything that has to roll out into the field, or wherever these printers are going to land, or these processes are going to land, so that it doesn't become a monument. Who's seen a monument out on the top floor? You know what I'm talking about? Man, we got all this great money, I put this great laser cutter out here, and man, it's just awesome, and it runs about 2 hours a year, and what does it normally make? Going away sign for people that just retired. Hey, congrats on your retirement. And it's this great laser etch thing, not being used for processes that it could be used for because it might not have followed these steps. And this is where the rapid sustainment office really pushes all this is you got to have all these steps in place so that you can get to here. Right? You got to be able to get to here. Otherwise, you're not solving the problem. We got to solve the problem. So this gets into everything from what's the environment to qualifying the machine. So when we build machines out on a shop floor somewhere, what has to be done? Is it documented? And how do we go qualify that piece of equipment or that process? Okay. Now you get out of here, get the safe use determination that we talked here, right? The technical foundation. There are a lot of steps to get there, but we have to get there. Okay. Now you're at the point where we can go through part qualifications. Right? So these are the application specific areas. So now we can design for the process, we can design for the material properties that are coming out of it, and so on. This is where the real solutions come to play. Okay? Not saying, hey, I've got this great technology, what problems do you have that I can go solve with it? But what problems do you have, and now what technology aligns with it? Okay? All right, any questions on tech requirements or certification? All right. Hopefully you're still interested. Maybe everybody's like, yeah, I don't really care about this stuff. Let's go to the next slide. All right. I'm not going to go through all of these, but what this shows is a bit of a timeline that you'll see over on the left. Okay. You might say, well, again, what's rapid? Right? Well, if it takes me X amount of months to get so many lots of material to get through the process, and we're able to hit that mark, that very well could be rapid. That could be as rapid as we can do with what the industry is producing right now. Okay, how do we accelerate that? Okay, we need to figure out ways to accelerate it. But what you're seeing here is the process development piece of it. This is where we get into really understanding everything that's associated with things like a laser cutter bed fusion printer or any other advanced manufacturing technology. too many times do organizations go and purchase something that's an advanced manufacturing technology. Again, I'll use it as additive as an example. They don't have the resources to put in and truly understand, how am I gonna tune this machine in? How am I gonna go through a process qualification? How am I gonna have raw stock coming in? How am I gonna do all this stuff? What happens is it varies the market in secondhand machines. So there are a lot of companies out there who are selling machines on the secondhand market because they made the purchase, they think it was gonna be a solution for what they were trying to do, and they just couldn't get there. Okay, so that's where the technology needs to come to play with the engineering side of things and with the need that's identified earlier in the process. Okay, you don't want to go buy a $1 million machine as an example and say, we'll find something to do with it, right? You need to find something to do and then find the process to go put your capital expenditure in the right place. Okay, so this is where we're looking. So we get into, again, these are more, I talked a little bit about this, where we have the physical properties and tensile. We get into our static, where you have shear strength, bearing strength, and so on. And then you get into your dynamic side of things, which gets into the fatigue and so on. Now, one thing you're going to see different here, and I'll point it out down here. Okay, as we get into the dynamic side of things, we're talking about things like fatigue. That's what's going to help us push these types of processes to be used in different applications. Okay, structural applications, critical applications. It's those types of areas that are going to be addressed for us to be able to do that. So today, show of hands. Can additive be used on aircraft today? Show of hands. It is, right? Now, is it used for everything on aircraft? No, not yet. It may not be used in landing gear. It may not be used in other structural applications. Okay, but it is being used. So as you start to cross over some of these areas, where you can say, hey, I've got tensile properties, or I've got something down in here, it just continues to open the aperture up as to what you can do with the technology, what you can do with that process. And then as you get further down on the chart here, it opens it up more for what you can do with the process. So more problems you can solve with this type of technology. So you don't want to wait until you get down here and say, okay, we've been through all of this and now we can use additive. There are offerings as you go through this process. Say, okay, yep, I want to use additive now in these types of parts. Okay, we've been through flame smoke toxicity on this polymer material. I can now use it in cockpit. Okay, so now you can start to open that box up. So there are offerings as we go through this process to be able to do that. But down here, just what I pointed out, machine versus as printed. So as printed gives you a surface finish. Machine gives you a surface finish. We have to be able to understand as we're going through these different types of material properties, we need to understand if I machine the part, how's that going to affect my fatigue life, my crack growth initiation, and so on. If I'm just using as printed surfaces, what's that do? And you might say, well, okay, well, we just machine it. Well, the whole point of having an additive process is to not have to do post-operation the machining on it, right? You want to print it, pop it off the printer, and go fly it on an aircraft, right? So that's where we need to get to. And so we have to understand a lot of this in order to be able to progress that forward. All right, so what you're seeing here then is over on the side, everything that plays into this, all the way down to the one I'm going to highlight here, which is AM design rule. Okay. You don't want industry to have to recreate, what can I do with these technologies? So if we can take the learnings through here and start to put them into a design guide, our engineers within the Air Force can now take that and say, okay, I know how I can use it. I know how to design it. I don't have to relearn it every time. I can go back and just start. Okay? And so that's what we want to do is make this as easy as possible in the Air Force network to be able to have everybody involved. Operators know where to go get preventive maintenance documents. They know where to go get tech orders in order to go print. Engineers know where to go get designs and material specs to design to, and so on and so on. And so building that network really allows us to crack that height curve. Everybody familiar with the height curve? You've seen it before? All right, so the height curve, I don't have a way to draw it out here, but the height curve is we got this great new technology, okay? And you start to sell it, and it climbs that height curve. And then it peaks and starts to come down into what you really can do, right? There's a lot of hype behind it, there's a lot of excitement behind it. A lot of times it'll fall into what's called the valley of death. So it'll peak, it'll come down, and then it'll start to average back out as to what you really can do with it. Our goal as we're working through these processes is never let that technology get into that valley of death. We want to go up and peak, and then come straight out horizontal with what we can do with it and use it. So setting the expectations early, what problems we can solve, and then allow us to go progress that so we can move it out into the field faster. Again, aligning with the rapid side of rapid statement office. Okay? All right, next slide, please.
Brian, can you go back that one quick, you had to say that AM design handbook, is there actually one existing?
There is one within the Air Force that we leverage and use. It's not a public released one yet. I know there's been conversation around, could we do one that could be? I just don't know where AMPO has landed on that. But there's been conversation, I know, I just don't know where they landed on it. So that, Jimmy, I don't know if that's something we can.
We can take it into action, but yeah, it's still kind of being worked right now.
Yeah. Yeah. All right, so where are we working? So I'm gonna, again, hone it down into additive manufacturing, because that's about the easiest way to kind of take this process and look at it going forward. So where are we playing? Okay, so metals powder bed, we've got EOS 290 side of thing, which is the smaller printer, but it's the workhorse. It runs a lot. EOS M404, if you're not familiar, that's a bigger platform, and it's got 4 lasers in it instead of 2. Okay, and so what we do, when we're looking at this one, the 404, is we're looking again, going through the material properties development. But on that particular machine, you have multiple laser interaction as it's printed. So the question is, when those lasers are overlapping each other, do you get the same material properties? If you don't, then we have to understand how those lasers stitch together so that we do get the same material properties. So we have to tune the machines in. Concept laser M2, so we have the series 5, Valdo Sapphire. So those are kind of the big players on the metal side of things. On the polymer side of things, you'll see it's 2 Stratasys machines, the 450, which is a smaller one. And then you have the 900, which is the larger, and then a section of high-speed extrusion as well. We have actually one that has 2 heads and one that has 1 head in that one as well. You might say, well, polymers really play a big part in solutions for aircraft. Okay, so we'll take a survey. Can they? Can polymers play a big place in that? Okay, all right. Yeah, I think they can, and we've proven that. Now, not only with things that happen in the cockpit, simple knobs, levers, handles, things like that, but we've also leveraged them to do, blocks and wedge spacers that are going to be outside exterior of aircraft mounting panels onto. And so being able to use those technologies and some of the Altem and Antero, being able to take them through the qualification phases and then use them out in the field, that's the key. If we had problems, we put solutions in place, we progress them forward, makes it easier. That's a pull. Jimmy talked about a pull and push. If you're pushing, it makes it really hard. If it's a pull, people are going to be asking you, when's this ready? When's this ready? When's this ready? So you want to make sure you have the pull, okay? And then coming down here, you can see the metals we're working in. We've talked titanium, we've talked aluminum, cobalt, stainless, nickel alloys, tie, and so on. So playing in a lot of different areas to solve a lot of the problems that we're seeing out there. And then same over here. You have other polymers for support equipment, masking, tool applications. These are the 2 big ones. That are really highly focused, they crash smoke toxicity, and they also could be very similar. This one could be very similar to other types of materials. Okay, so stuff that we're using on aircraft now has a little more strength to it, and we can actually use those for those solutions. Right? So phenolics as an example, we can use Antero to take place as a phenolic type material. Not only does that solve the problem, but it also helps get the operators and so on out of an environment where you might be machining a phenolic, which is a carcinogenic as you do it. So you're solving a lot of problems with one pocket. Okay? You go to, there might be a next slide. Let's see. Yes. So I'm going to invite Mr. Luke Schultz up here after I ask if there are any questions. We'll talk a little bit about LC. So any questions on the material side of things, all the excitement that happens there?
Okay, so Brian, thank you for giving an excellent presentation on materials side. And you asked a question at the beginning about the difference between advanced manufacturing and additive manufacturing. So if we revisit the history, advanced manufacturing is mostly use inspired. Additive manufacturing, people invented the machine and let's see what we can do.
That's a beautiful way to put it.
And so,
absolutely.
So, and we are not there yet where use inspired research should create revolution on the machine side. That I'm not seeing. I mean, we are playing at the hands of machine manufacturers.
I think I'm not gonna disagree with that. I'll agree with that to some extent. There are a lot of, it's more academic and research partners who are playing in that space for how we leverage the next generation of what I would call additive technology or those types of technologies. But you're right. The machine manufacturers now are the ones who are kind of leading the way with where we're trying to go. And that's what puts us in that situation of then having to find a solution for what we're doing here, right?
Yeah.
And so, yeah, I think, but the big thing is with the manufacturers though, is they push the technology pretty far. And the results that we get from a materials standpoint in almost every aspect are very, very similar to raw materials. So they push the envelope on the technology to be able to get us close to where we need to be material properties wise. But you're right, we're still a little bit at the hands of where they want to go with it next, because those are the bigger investors in the industry.
I mean, that may be a subject for James next for later. To bring 3D printers and additive manufacturing machine makers.
Yep.
Come and mix with, you know.
Now, to address that further, so we work very closely with the machine manufacturers. As you saw, we, on the metal side, let's say we had EOS up there, we had, Concept Laser and others, Bellow and so on. We work very closely with them. Now, the goal is to be able to take off-the-shelf technologies, right? And be able to progress those through what we talked about here. Okay, industry-wide, be able to push them through. But we still have open architecture on a lot of machines so that we can go in and work with them to be able to adjust as needed, to be able to put solutions in place as required. Okay, so we have open architecture on the machines to be able to change, some of the laser parameters. Pretty much anything that's not going to cause a safety issue, oxygen levels in the machine, or whatever it might be, anything that's not going to be a safety issue, they'll let us go and adjust. We'll actually go back and work with them and say, hey, this is something that we find isn't working well or something that needs adjusted. And many times they've actually made the adjustment and actually put it back out in their next iteration. Okay, so an example of this is several years ago, we were working with them, and if you're familiar with additive manufacturing, there's a cool down period as you're going layer to layer to layer. Okay, and so we have to take a look at that. We have to understand it. And the software wasn't allowing us to cool the part appropriately before the next layer was done. So we had to go to an offline way to do it. We had to find a solution. So we called the manufacturer and said, hey, your software is not letting us do what we need to do in order to get the properties we need. And they said, oh, well, we can fix that.
Yeah.
And so their next revision of software that came out had that fixed, and they adjusted it for us to be able to do that. So I think it's a mix. It's being able to have understanding of use of the equipment so that we can work with the manufacturers, and I think they're open to help progress that technology forward.
Thank you.
Yeah, absolutely.
My question is going back a little bit to the demand signal that you get and referring to a couple of different places it might come from. Might be from a regular maintenance depot versus a forward operating base where the need might be much more urgent. Do you see breakout out of that hype curve for technologies happening when a demand comes from a forward operating base for a more urgent need compared to regular preventive maintenance cycle?
So I don't know, Jimmy, if you want to talk that at all, but I think the demand, while it's coming from many places, something that might be happening more forward operating might be something simple. And any of them, it might be something simple. It might be something that, hey, I need a cap or a cover to fix this, or I need something to go do X, where you can use a lower grade or lower level of technology to just solve the problem and do it because you're playing in that different box that I talked about. Now, when you get into that higher level demand signal where you have more demand coming in, that's where we have to then make sure that we're covering the bases appropriately to ensure that we're meeting the needs of whatever the end use of that part is. Okay, so quick turn, that's the kind of stuff Jimmy and team look at. It's like, hey, what are the parts that are quick turn? What can we do? And do we have solutions now? And we'll progress those forward. If we don't, that's when they go into his pipeline that he talked about and says, okay, now we got to find a solution for these types of things, and here's how we're going to do it. So I think it varies at all levels to understand how we respond to the demand signals. I don't know, Jimmy, if you've got any other input on that.
I think that's pretty accurate. I think when you see a demand signal in an enterprise organization, as we all know, they're all different. And then it also depends on the criticality and the operations need, right? Because if I have someone who's like, I need that, I'm like, well, you can go to Staples and buy that, right? Or Amazon. But there's been other pieces where we've been able to use additive. I'll just try and keep it at a low level. There was a piece on an aircraft that was in the wrong spot, so every time the pilot got out and kicked it, it essentially down the aircraft for like 3 days. What do? You just put a polymer cover and put it over it, right? Like, so you can do innovative things with simple switches, but not everything has to be positive, right? Like if you're in an ACE environment, you don't need all this technology. Maybe you just need the TOs with laminate over it, so when it's on, you can wipe it off, right? So I mean, there's different ways to go about innovation. Not everything is a tech push. We like the tech push. We think there's a lot of value in it, but it just depends on the demand signal. How fast can I get you something that may be different than what you're doing?
Right. Any other questions on how we can take some of these processes, materials and kind of tune them into the extreme environments? But a lot of the things that are going to be happening where we talked about in extreme environments are going to go through different types of testing, and you can see up here. What you saw was a lot of baseline, so that's some of the specialty testing that needed to be done. So as we get into extreme environments, we've got to push that even further. So it's just got to be, it's got to be more critical as we drive that forward and open that aperture up as well.
I did have one more question. So when you're talking about the rapid sustainment, is it more about vehicles which are carrying personnel, or are you also looking at munitions and hypersonic drones, unmanned stuff out there?
Everything.
Okay,
Not getting into the detail.
yeah,
So if you try and spell sustainment, very hard, right? Because it encompasses anywhere from if you look at the statutes and everything, it could be integrated base defense, right? Or it could be repairing the aircraft. So the world sustainment with all the abilities, reliability, maintainability, availability, then the integrated climate support elements, you put all that together and you go, all right, what do we need to do, right? So we do look across the spectrum at all the different, I'll say, mission threads, how we can use technology. It's not just on parts alone, there's other applications. So I'm gonna give it the loop, but the QR code, I believe, takes you to my homepage, which has a connect to us. So you go and there's a bunch of different things. It allows you to get in contact with the RSO and then provide your information. We have a bunch of different teams that we can respond to. They didn't have a QR for LCID, but LCID is our main event here in the Dayton area that Luke's about to tell you about. That's where I've been pushing a lot of small businesses, maybe not converted across the US. You'll find that every PEO is there and a lot of senior leaders are there for these types of discussions with work.
Okay, well, I got one more question.
Just one question. So, just a general question, like RSO also focuses on in-space manufacturing,
I'm sorry, aerospace?
and in space, on orbit more manufacturing, and like low Earth orbit.
I don't think that's as much in our wheelhouse, so to speak.
You can. I'll leave it at that.
Okay.
Because there, some of these materials are used in various applications, whether it's low over, high over, or just on the ground, right? So I think there's capabilities, but that's mostly within, let's say, the space domain, right? Space Force is what they do, but we partner across the services, and then obviously Space Force is part of the Department of the Air Force. So we have a relationship with them.
So before I turn it over here, I know several of you had talked a little bit about kind of the digital world and being part of the AI side of things and digital and so on. Everything we do in these advanced manufacturing processes starts in the digital world. So we have to play with the digital side of things, which connects into all of the AI, machine learning, all of that starts to play together when we pull this space, the thread on this space. So it's not just material properties, things like we talked here to get through the process. There's a lot on the digital side that really can come to bear as well. So if you're in that space as well, LC is a great opportunity to be able to continue conversations because all of that plays together. Okay, all right, turn it over to you. Okay, thank you.
It's great. Thanks for your support. I really appreciate it. So my name is Luke Schultz, Director of Small Business Programs for Air Force Lifecycle Management Center. So they spoke about LCID Lifecycle Industry Days. It is AFRL-CMC's preeminent event. It's going to be the week of July 29th, the 30th, and 31st. It's combination with Air Force Research Labs. They're doing their right dialogue with industry too. So a lot of great speakers there. I imagine they'll be talking about great power competition, re-optimization, which by the way, if you go to the AFRL-CMC main website, they have a tab click on it, re-optimization, it has all the articles about the great power competition, things that are going on there, some of the changes, things like that. Just earlier today, I actually recorded a small business video to talk about LSID, so hopefully that will be out on the site pretty soon. From a small business standpoint, we're looking to have 3 panels. One panel's going to be all the small business directors within Air Force Material Command are going to be there. So the Sustainment Center, I don't think Test Center can make it, Research Labs, Air Force Material Command. My team will be there. So we'll have a panel, I believe, talking about reducing barriers for small business. We'll also have another panel other than small businesses, so your Boeings, your Lockheeds, companies like that, that will talk about doing business with them, subcontracting opportunities. And what's going to be unique with this year is we're looking to have that second day. So I believe the other than small businesses like your Boeing, Lockheed will be on the first day. Then there's going to be matchmaking opportunities to sign up to talk with those companies one-on-one, which will be great. Then the next following panel after that, we're looking to have the innovation leads talk about the various opportunities, kind of successes, and then you'll be able to speak with them. Really, LSID, we're really looking at it this year to be really kind of a strategic partnership, networking. It's just a great event and a wealth of information. The next thing too, we've spent a lot of time on the Air Force Lifecycle Management Small Business website. So you can just search AFL-CMC Small Business Office website. We link expiring contracts for the next 3 years. There's an Excel spreadsheet you can look at. There's other useful information out there like the upcoming colliders. I know that you guys love. I mean, these are great because they're hybrid, so in person and virtual too. They've got some coming up on demystifying source selection, demystifying the FOM process. Now I have a facility clearance. So what, or now what? There's going to be one with AFMC small business directors. There's going to be one I'm really excited about is the operational imperatives and great power competition. So a lot of great events out there, but yeah, I'm putting a lot of time in the website to share information for you guys. And really look at us to be your entry door to doing business with Air Force Lifecycle Management Center. But that is our preeminent event. POs are going to be there. You can sign up and schedule one-on-ones with POs. So, hey, I want to talk with, I know Jimmy's going to be there. And last year you attended, you met with various small businesses and other businesses.
I think I had 25 speed dates.
Yeah. So, but understand when you sign up for those, and if you get the opportunity, understand what your capability is, how you can apply that capability to the organization. So if you go out to the AFL-CMC website, there's an organization list. You can click on that, click on it again. It'll list all the mission directorates, the enabling directorates that are out there. So you can go to their website and be like, okay, what does ISR soft do? Rapid Sustainment Office, they have a great page too. So a lot of great information, and I know Jim, you've been at LSID, I know Bill Harrison's been there. It's just a great event, and it's really our preeminent event for there, and it's going to be at the Dayton Convention Center this year. So the only other thing I want to bring up the week after that, so the RSO has been doing a lot of work with the Air Force Sustainment Center. So that week right after that, you're going to be tinkering the primes out of Tinker. And Ronnie Hobbs is a small business director out there. I'm looking to attend it this year, so I'm hoping to make it. Plan on traveling out there, and that's another great event too. So I know you guys are working hand in hand with them. It's the same everything like that. So, but yeah, if you have any other questions or anything like that, please come see me. We'll have that out and look forward to speaking to you. Thank you.
Yeah, thanks for having us. Appreciate it. Hey, Kelly.
Hello. Can you
What?
guys see me?
Yes.
Okay. So I am, my name is Callie, and I am a research chemist here in the USACE. So just to get started, I wanted to give you guys just a little quick brief about me as a person. So my name is Callie, and I actually grew up off the coast of Georgia in a small little town that you may have heard of called Savannah. And from there, I moved to Atlanta to pursue my bachelor's in chemistry. And then I ended up changing states, a couple of states down the south in Louisiana, where I obtained my PhD in electrochemistry at the Louisiana State University. So what's cool about being an electrochemist and having just the background knowledge of how electrochemistry works and how redox reactions occur, I am able to start shifting my focus to corrosion. And something really special about that is my thesis presentation was working on trying to develop a technique to electrochemically reduce chromium-6 to chromium-3. So chromium-6 is pretty toxic, but it's really, really good in terms of preventing corrosion. But due to the downfall of the toxicity, the DoD is really trying hard to move away from using that form of corrosion inhibition. So the DoD is a huge, giant conglomerate, but the United States Army Corps of Engineers is just a small part of the big army. So to get started, I'm going to change the page here. And tell you guys a little bit about just the Army enterprise. So we have Big Army. That Big Army has multiple different branches inside of it. I believe the Coast Guard is a part of Big Army, as well as the Marine Corps. Don't quote me on that second part, but I'm fairly certain the Coast Guard is a part of the Big Army. So Big Army has several different options, and then the small arm of Army has the Science and Technology Enterprise. So this science and technology program expands several different options. So here we can see that we've got the Army Futures Command, the Space and Missile Defense Command, as well as just the headquarters of the Army, where the Army Research Institute is located. And then as we move further to the side, you can see that there is some non-traditional laboratories that are a part of the whole S&T program. But what we're here to talk about is the U.S. Army Corps of Engineers. So USACE is a very small part of the Big Army. And what's really cool about USACE is that they have about 12 different divisions throughout the entire United States. Each of those divisions has small little departments throughout, and those are all focused on civil works projects. So maintaining waterways, maintaining roads and bridges, and a big thing that the Engineer Research and Development Center works on is trying to help the USACE figure out ways to better our infrastructure through research and development. So from the USACE, we then have a small little subsection called ERDIC. So ERDIC is the Engineer Research and Development Center, and throughout, I'll just be calling it ERDIC, but just so you know, that's where the R&D happens for the Corps. So the ERDIC is split up between 7 different labs. So at the bottom, you can see that there is the cold regions research and engineering lab, the geospatial research lab, the construction engineering research laboratory, coastal and hydraulics laboratory, information technology lab, the environmental lab, and the geotechnical and structures laboratory. So basically, the takeaway from this slide is that ERDIC is going to be one of the second largest Army research and development organizations for this big Army S&T program. The other programs that are pretty large are the Army Future Commands, as well as the just Army Research Lab in general. So that's where I'm at here. Does anybody have any questions on the breakdown before we move forward? Because if not, we can just skip to the next slide.
We're good, Kelly.
All right, next slide. Okay, so to just tell you guys a little bit more about ERDIC. So ERDIC is a world-class R&D organization that strives to discover, develop, and deliver new ways to make the world a better place, while also attempting to help the warfighter and the infrastructure within the United States. So here we have 7 laboratories that you can see that are kind of all scattered throughout the United States. So if we start at ERDIC headquarters, that's going to be located down in Vicksburg, Mississippi. That headquarters is where our commander and our director sit, and they oversee the entirety of ERDIC. And within the headquarters space, we have the Coastal Hydraulics Laboratory. The Coastal Hydraulics Laboratory mainly focuses on hydrology, river engineering, coastal sciences, as well as navigations and hydraulic systems that help reinforce our waterways. So say the Mississippi River, right? The Mississippi River stretches from, I believe, Michigan in that northern area and goes all the way down through the middle of the United States, and then it dumps out in the Louisiana at the Gulf of Mexico. So within these river systems, there are a bunch of dams, and the Coastal Hydraulics Laboratory really focuses on how they can give the best R&D to make our locks and dams, our waterways more effective and clean for the transportation of goods. Next, we have the environmental laboratory. Well, the environmental laboratory focuses a lot on different chemistries, different environmental processes, as well as engineering, to basically look at environmental systems, wetlands, coastal ecologies, and try to figure out how we can best provide the information needed to make the environmental system a little bit easier on everyone in terms of invasive species, in terms of erosion of the coastal ways, because I'm not sure if you guys are familiar, but down in Louisiana, they are currently slowly eroding away. And if climate change is something that you guys are passionate about, EL is looking at different ways to help the erosion. So say in my small town of Savannah, there's an island there called Tybee Island. It's a really big port. So as these giant container ships move through the Savannah River to get to the port, they're slowly taking away the surfaces, the outlining of that island. So a major project that Engineering with Nature is doing is they're trying to take the dredging that occurs throughout the United States and figure out what places can they use this dredged material to pack on the coastal ways to help like build it up and stop the erosion of the coastal lands, which I think is pretty cool. Then we've got the geotechnical and structures laboratory. So that is GSL, where really they just look at the structure mechanics of different types of concrete materials, engineering those concrete materials like airfields, pavements, roads, bridges. They really focus on the infrastructure that has to do with concrete. And then ITL is the Information Technology Laboratory, where they do a lot of computational analyses, some software that is based on scientific models, as well as working on sensor integration, because sensors are kind of up and coming in the world right now. And so we have a lot of work trying to develop more sensors that are able to detect things like chemical warfare agents that might be in the waterway systems, the sewage systems, wherever the warfighter might be. How can they use a simple sensor, put it in the water and see what is in it? And that way they know, hey, this water is clean, we can use it, or it's not dirty, maybe we should use something else. So those are the 4 main laboratories that are located within the headquarters, the main station of ERDIC. And then we move forward to the Cold Regions Laboratory. That is up in New Hampshire. And the Cold Regions Laboratory mainly focuses on like bio, geochemical sciences, as well as like cryosphere solutions, to really look at complex environments and how the structures are surviving within these really extreme environments, like say Alaska or something, where it's cold. If they have paintings, how can they, if the coatings, like how can we make the coatings ice phobic, so that way we can no longer have to worry about chipping away ice, and in the process of chipping away ice, you're then damaging the coating system, which leads to corrosion. In the DC area, the DMV area, we have the Geospatial Research Laboratory. They really just focus on geospatial analysis and information to have just structures. And I think the Geospatial Research Laboratory does do some outer space research, which I think is pretty cool personally. And then we have the Construction Engineer Research Laboratory. So the Construction Engineer Research Laboratory does a whole lot of things in terms of construction itself, and we'll talk about that in the next slide. But additionally, we have field offices throughout the United States. There's a couple in Alaska that help us with our Cold Regions Lab. And then one really cool laboratory that we have that the Paint Lab works a lot with is the research, the field research facility that's out in Duck, North Carolina. So it's on one of the barrier islands outside of the coast of North Carolina, where it's a perfect place for corrosion to happen, but it's also a really good place for other laboratories like CHL to be able to have a external research site where they can do their field work and field analyses to see how basically the surfaces of islands are changing over time, which leads back to erosion of our coastal areas. So really one giant conglomeration organization that focuses on many different aspects. But what's really cool about ERDIC is that we can all work together on specific aspects and use each other's expertise to help solve problems. So this is just a breakdown of ERDIC as a whole. It started in, I think, 1927, when there was a great flood down in the Mississippi Delta, and that's where CHL became involved. And then slowly, as the you know, as things started progressing, wars started happening, you know, domestic attacks started happening, climate change is a thing. We start to add on to all of these laboratories. And in about 1998, we all decided to come one big giant ERDIC instead of just having 7 random laboratories within the USACE. So now we are a one ERDIC, and we use all of these laboratories to help the warfighter and help the infrastructure within the United States. So on our next slide, I can jump into the Construction Engineering Research Lab. Oh, well, sorry, side note. Quick little side note here. Just to show you guys some cool things that ERDIC actually does. So we have premier R&D facilities that cost roughly around $2 billion in infrastructure to actually be able to maintain and build these environments. So if we look at the top left corner here, we've got a cognitive ecology and eco-hydraulics research facility. This is actually going to be one of the largest centrifuges that is located within the world, I think. And so we're able to put a lot of samples in, centrifuge them, and figure out what happens when we have a supernate and a supernate form within conicals, and how does the separation really work. Below that, we've got our supercomputer, which is located here in Vicksburg, and that is for ITL. That supercomputer has the ability to do a lot of different cool things, and ITL really focuses on doing simulations that help other laboratories figure out what would happen in terms of things that might blow up or structures that might get hit. How can we make a model for that? And from those models, can we learn from them? Right below, we have a heavy vehicle simulator called the Titan, which is basically just a big railroad where where GSL builds different types of concrete, and then they take that little train and they just pull it back and forth to see how long it takes for this concrete cement to be damaged. So that gives us a little bit of ideas of how we can better our road systems throughout the United States. CHL has a ship simulator, so that gives us a little bit of ideas of how, as we move our ships throughout the United States, how is it affecting the coastal ways as the ships move through, because at one point, I think CHL did a study based off of, again, my small town of Savannah, where they found that the ships that are moving through to the Savannah River, to that seaport, are actually eroding away. So they're able to simulate it to figure out what's going on and how we can best protect our systems. Below that, we have an advanced load simulator, so we can throw some things inside of it and see if we say use TNT or something and just pop it on the surface of the concrete. Is it going to actually survive that explosion? And it's done within a controlled environment. To the right, we have cold climate chambers, which basically tells us if we have a coating or if we have some type of material that we want to see if it is actually going to be useful in these environments, we can simulate that in these chambers to be able to see if it will withhold. And if it doesn't, then we have to go back to the drawing board and do a little bit more research before we can actually do some development. In the middle is the robotics research facility in Searle, and they do a lot of cool things in terms of building robots and building unmanned vehicles. I will say this robotics research team does do a lot of work with ITL. So just to say, like, this is actually a collaboration within 2 different laboratories within ERDIC. So we really work on trying to collaborate and use everyone's strengths to make the best product we can. And then at the bottom here, in the right side, we have CHL, which is a physical model of a river. That river will have a dam on it. They can look at how the water flow is actually moving to the dam. Is the dam being affected within this water flow? And they can look at it for many different waterways throughout the United States. So bringing it back to the robotics research facility at Searle, now the next slide is going to be about Searle, and I can give you a little bit of lowdown about that because that is the laboratory where the paint lab is centered. So next slide. Okay, so the Construction Engineering Research Laboratory is one of the 7 laboratories. It is located in Champaign, Illinois. And so in terms of workforce, we have about 250 employees. Most of those employees are going to be engineers and scientists, and it ranges from what type of education they have, whether that's a bachelor's, a master's, or even a PhD level. So we try to be very inclusive with who we are able to hire because we encourage further education. And so if you say come in with a bachelor's and you've worked at ERDIC for about 3 years, you can then move forward to try and get a master's or a PhD, depending on how those programs move forward. So like for me, I didn't need a master's. I just went from my bachelor's to my PhD, but other fields are different. But so that's really cool. And so out of the 250 people that work at Searle, most of everybody is going to be an engineer or a scientist. So Searle really focuses on environmental processes, ecological processes, as well as land and heritage conservation. We really want to be able to have a really good way to sustain energy and be able to say, if we have some solar powers, can we harvest that energy and use it for other things? Because I know that that's a hot topic here in the science world. Another is materials and structures, as well as engineering processes. So you can read the core competencies within there, but I will say some cool things that Searle has is that we have the capability of doing concrete 3D printing, and those concrete 3D printings are going to be awesome when the warfighters are out in the field and they need to build a structure. They can do so by taking that 3D concrete machine and building up a structure that will serve them purpose for shelter wherever they are. And then here's another picture of the robot facility. They have a really nice large tent that they can do a lot of different work on their robots. And then lastly, one cool thing that we have is a earthquake and shock simulator. And this table is actually one of the largest ones in, I will say, the world, could be just in the United States. Don't take my word for that. But it's really cool. So that simulator, we can place objects on it, say like a concrete slab, and simulate what an earthquake would be like and be able to see, is this material that we're putting on it going to be able to withstand the forces that occur naturally in the world, like an earthquake. So that's basically the overview of ERDIC and Searle. Before I move forward and jump into the paint lab and what we're really here to talk about, does anybody have any questions?
We're good.
Awesome, cool. So I'm ready for the next page. Okay, so this is my bread and butter, and this is what I have come here to talk to you about. So USACE within Searle has a paint technology center of expertise. Now, this center also coined PTCX. I will say one thing, if you don't know, the government and all of the DoD love acronyms. So I tried to make sure I've explained the acronyms before using them. But I think moving forward, I will refer to the Paint Center as either the Paint Center or a PTCX, whatever we feel like. But so here at our center, we want to maintain state-of-the-art technical instruments and facilities, as well as our members of our team staying experts in whatever section they choose to want to be a part of. So really what we do is we try to focus on paints and coatings that we can use on military and civil works infrastructure. And in doing so, we're able to guide many different organizations on the specifics and how to installate paints and coatings. So here are a couple of cool pictures of everybody out in the field. So to the left here, at the very top left, you have someone that is working on a structure, and this is essentially I believe he's a coating inspector, and this is him going through the testing to make sure that he can get the qualifications to be that type of inspector. Below that picture, we have Rebecca Wilson, and she is doing some out in the field work, looking at the structure, seeing what coatings look like, and making sure that everything is up to standard, so that way we can try our best to limit the corrosion that happens on these steel structures. If we move back up top, here's a couple of more pictures of being in the field. This lady in her Converses is collecting some mold. In the middle, this is a thermal image camera, so you can be able to see the differences in heat in your surroundings. As we move forward, that is some form of very dusty installation where we had to make sure we had our correct PPE on to make sure our lungs were safe as we try to not inhale all of that dust around there. To the far right, which might be the far right to you guys. If not,
Yes, it is.
it is. Okay, awesome. Great, thanks. So here we've got somebody, he is testing the moisture content that is on a cement wall. And that is something pretty cool that we're able to say, okay, this wall is not coated at all, and it's retaining this type of moisture because uncoated concrete is very porous. So within those pores, they're just going to eat everything that's able to come to them. And then as we go to the far right, that is another image out in the field of Rebecca looking at some type of infrastructure that is within the waterways that is covered in an invasive species called zebra mussels. And we'll get into that as we move forward on the maybe a few slides from now, but I'm ready to move forward. Okay, so meet the team for the Paint Technology Center of Expertise. So here at the far left corner, we have Dr. Rebecca Wilson. She is going to be the Director of R&D, and she is a research chemist. So she's all about corrosion and figuring out how we can go about to find the best coatings, the best inhibitors, how we can use our chemical background to actually try and stop the electrochemistry from forming. And then you've got me. Army, I'm also a research chemist. I've dubbed myself a corrosion chemist because that's kind of like my field of expertise as I am a member of this team. Then we've got Carolyn, she's a mechanical engineer. We've got Elizabeth, she's structural engineer. Brooke Divian is going to be the director of field relations. So those field relations are working within the districts of the Army Corps and seeing how they are going about their repairs on the infrastructure and if there's anything that she can do to help them with however much help they would need. Below is her technician, James, and he does a lot of paint quality samples to make sure that the industry is actually formulating paint that is going to withstand and hold the specifications that are required for the USACE installations. As we move down to the left, here we've got Drew Miller. He is a senior R&D technician. To the right, we've got Kyle. To the right, we've got Jaime. Both of them are R&D technicians as well, and they basically are a little bit below Drew, but Drew is going to be that main technician that is going to divvy out the work to the other technicians. This no-name picture is Madison, and she is a historical architecture, and she provides a lot of guidance on different types of structures. And this is our whole team, and we work really well together. And I just want you to know that this team is composed of chemists, composed of veterans, a combat engineer, structural and mechanical engineers, as well as sprinkled around with some civilians. So we are doing really well and being able to see the full picture of different sides of the DoD and how we can help not just USACE, not just the Army, but all of the armed forces, like the Air Force that we just heard from. So now I'm going to go into some projects that we have, and we can go to the next slide. Okay, well, all right. Obviously, I wasn't like super prepared with all the projects and the way the slides were adjusted, but we're going with it. Okay, so overall, we want to provide paints and coatings that are going to be resilient and sustainable so that our infrastructure can last as long as it can. And we're doing that through R&D and field support. So some of our core functionings that we do at the paint lab is doing education and training. So we have courses where people can come in from the districts and learn what paints and coatings do and how they can best look for defects to continue maintenance. Our field support is doing the exact same thing. And then the quality assurance is what I mentioned in the previous slide, where James, the technician, he makes sure all of the paints are up to standards. And we do give guidance, criteria, and policy. And in that, we really help the Army try to have the best policy out there so that we can make sure our infrastructure is sound. But what we really came to talk about today was R&D. So our research areas involve a whole bunch of things, from green coating technologies to energy efficient technologies and removal and applications of coatings. But what I'm going to focus on today is corrosion, and we'll get into that as we move forward. But one thing I did want to note is that we do have a lot of collaborations going on within the Paint Center. A lot of those are the government. So we've got the Army Research Lab, the Naval Research Lab, the Naval Airfare War Center. We currently have started working with the Air Force Civil Engineering Center and have ongoing efforts with the Joint Munition Command of the Army. In terms of universities, university, we do have collaborations with the University of Illinois, where we look at solar powers as well as some different types of unconventional countermeasure research. North Dakota State University, we do a lot of universal flexible coatings as well as fasteners. And we do have a project going on, which is looking at trying to create a predictive model for coding life cycles. And from that model, can we tailor these paints to extend the life cycle based on those feedback from these models. And then similarly, Acron, we are working on reliable coding service life predictions. And from our predictions, we want to be able to consider some types of uncertainties that can come through during the life cycle of these coded structures. And that is just a little snapshot of what we do with the university. And then we also have industry partners where we work with them to make sure their paint is up to standards. And that's where we're at for this one. Now, everyone, the next slide is going to be where we get into a couple of different subjects of our research, I'm hoping, but I'm pretty sure it is. So to do our research, I was wrong, but that's okay. To do our research, we have a couple of unique facilities. So we've got a shielded analysis chamber. So that's going to be EMF blocking. So if we needed to collaborate with someone that's looking for maybe a coating that has special formulations in it that can shield EMFs, we have a analysis chamber that can help us figure out if that's true. Throughout the entire world, we have exposure racks. Those exposure racks are going to help us see if we painted a coating on a panel, we left that coating to be exposed naturally, how does that affect the coatings? We have a large lab for our R&D. So here you can see that just like this really large open center, that open center becomes crazy sometimes, but I will say that's a lot of room for us to be able to expand and do several different experiments and several different projects to try and figure out, what to do. So we're always trying to multitask. We've got a lot going on. And then lastly, we have a really cool accelerated weathering facility where we can use guidance from the ASTM and the ISO to be able to cycle through painted panels and see how they mechanistically can be durable through salts and humidity fogs, as well as UV exposure and freeze drying. So that way we can kind of like look at how the panels and the paints and the coatings can do in an accelerated fashion. Once we have an idea of that, we can then put them out in an exposure rack to, test out the waters, see everything that's going. Now, for sure, I know the next one is now some projects. Does anybody have any questions before I move forward?
Good.
Okay, cool. All right. We have a bunch of cool instruments, right? So we've got a UV-Vis, a spectroscopy, gas chromatography. We have a 3D measuring machine where we can look at models 3D wise and be able to see what's going on. We have the SCM, which is where we can look at things at a microscopic level. And then we have a digital microscope and elemental analyzer. All of these things help us when we're trying to determine corrosion, how much corrosion is being formed, is it creeping underneath the coating, and from there we can see a lot of cool things. Now, I'm quite certain this next one's actually projects. So if we go to the next slide. Okay, all right. So I was wrong like 3 times, but now I'm right. So now we can get into the fun nitty gritty stuff of like some cool things that we're doing at the lab. Now that you have just a general idea of what capabilities we have at the Paint Center and just what ERDIC is in general. Okay, so first we are looking at different coating removal techniques. So if you look in the far right corner, this is Carolyn. She's our mechanical engineer, and she is sitting at the bench top using a chisel to chisel away the coatings on these paintings. And I will tell you, it takes a lot of elbow grease sometimes to get those coatings removed. So can we make this process easier? So we have 2 different options here. The first one is using atmospheric plasma. So no, that's reversed. Apologies. The laser guided is to the left. Atmospheric is to the right. I apologize. So laser guided removal is basically a machine learning guided laser, and that laser is going to slowly remove different layers of the coating. And as soon as it hits some form of corrosion, it will stop so that we can move forward and analyze that. So this laser guided process removes the need for manual scraping and also are able to expose corrosion. This is really cool. So if the coating is delaminating and we have corrosion in the middle of a delamination, we can figure out, okay, at what layer is the corrosion happening? What is going on? Is there proper adhesion? Is there not? So now the atmospheric plasma, apologies for the typo, but we are human. The atmospheric plasma is to the image to the bottom right, where you are using a plasma gun to basically apply cold cap plasma to these panels, and it easily removes all of the organic material. So coatings are mainly going to be some form of polymer matrix, which is going to be long carbon chains, organic material. So what we're left with is some of the inorganic material like the pigments and the primer. So pigments are usually titanium dioxide, and a really good primer that is commonly used is zinc. So we can easily remove the organic material, but the inorganic material is a little bit more challenging. So we have to look into better solutions for these 2 types of technologies to help us better remove our coatings. The next slide. Okay, so another cool thing that we are working on is some blasting media. So in order to apply some form of a coating to a substrate, you need to have some sort of surface profile. So that way when the coating is applied, it's not applied to a straight surface, and it gives the ridges and the peaks and valleys for the coatings to be able to really seep in and actually adhere better to the surfaces. So one thing that we're looking at is if we use different types of blasting media, are we able to find a correlation to mitigating properties? So on the left here at the very top, you can see some black images. That's just our normal blasting media of aluminum oxide. And then below you see some really pretty pink minerals. These minerals are garnet. And so if we use garnet and we blast the surface for preparation of the garnet, we can start to see that these things can be embedded into the surface. This picture in the middle has a circle that says potential material transfer. So what we're seeing is if we use some form of garnet, that garnet is actually going to embed itself into the steel profile. And hopefully have some form of corrosion protection. So we're in the process of trying to figure that out. But if you look at the images to the left, you can see some panels. All of these panels were treated by different grit sizes of the garnet material. And what you can see is that there's some that don't really have any rust creep under the scribe, and then some do. So this is kind of giving us an idea of what is the actual size we need to be able to effectively embed material, but also prepare the surface to hopefully have these corrosion mitigation properties. So looking forward, we're trying to see if we can figure out some type of classification system and actually be able to pinpoint, hey, if you use this, then this has this type of properties to help mitigate the corrosion. And so that's something that is really cool because garnet in itself has different types of metals inside of it. And if we know anything about redox chemistry, metals make it happen. So by having some form of a metal embedded in the surface, is it helping inhibit corrosion? And that's where we're at in terms of trying to figure this out. The next slide, please.
Hey, Callie, we're running just a little late on time, so if you could hit the 30,000 foot view in the next 5 charts, that'd be great.
Got you. I'm gonna talk real fast. Thank you, guys.
You're welcome. It's not your fault either. The RSO went a little over time, so sorry. Thank you.
Okay, so all right, this is our crash course now. Okay, so basically another form of corrosion is biocorrosion. So we have these invasive species called zebra mussels. The zebra mussels like to attach onto these structures in freshwater systems, and they slowly eat away at the coatings. As they eat away at those coatings, they then leave a nice center of exposed metal. That exposed metal starts to corrode, and then once corrosion starts, the whole system it spreads out. So can we figure out a way to make a coating that these zebra mussels aren't interested in? I don't know. We'll see. Next slide. Okay, so green technology coatings. So what you can see here in this image is a bunch of different coating panels that are coated with different materials. And they look gross, right? Because corrosion happens. But if we take away the painting, the coating, what we can see underneath is that some don't have a lot of corrosion at the scribe where we put over the painting. So that in itself, really cool. What we want to do is we kind of want to step away from vinyl. Vinyl is very restricted these days in terms of what we can use it in. So if we can find alternatives to vinyl that have the same performances, we're able to hopefully lower the volatile organic chemicals that come out of vinyl by replacing it with something else, which makes it green, right? Okay, next slide. Okay, so this one's really cool. So we are working on a joint effort with the JMC, which is the Joint Munition Command, where we are going into different magazines where these magazines are covered by the earth. And we're trying to figure out how can we mitigate the corrosion? I mean, the mold that's forming. So if you look at these very bottom pictures, like I would say the bottom second to the left, that is a beautiful picture inside the magazine of nasty, nasty mold just building up on the walls. So what we did is the next picture, we took 2 boxes and we painted those, we squared out those boxes, and then we used a formula called Nav Clean, and we scrubbed the mold away. And that far right box, you can see that there is no mold in those boxes. So as we move forward in a couple of months, we'll keep checking on it. And if that is actually a really good chemical to use, then it's possible we can really work on trying to mitigate the mold that forms. And also not only mold is forming because it's hot and humid inside these magazines, but also corrosion is forming. So if you look at that picture on the right above the two pretty boxes, you can see that there is corrosion forming on the metal banding that they use for the ammo boxes. So I personally think that this is a really cool project. Yes, moving forward. Oh, I think I have 2 more slides after this, and I'm certain on that. Okay, so Guam is a very small island out in the Pacific Ocean. They are having a lot of issues with their radar equipment, so their airfield damage repair equipment, like their excavators and their bucket trucks, all the big equipment, and it's all corroding away because it's this small island that is pretty hot and it's got a lot of salt in the air. So we are working on trying to get with the Air Force to visit out in Guam and figure out what is the actual state of the corrosion and how can we fix it. How can we provide guidance, because it's expensive to ship a lot of things out to Guam, and if we can find solutions to continue the life of these machineries, it'd be really awesome. So the last slide is a similar feat. So Kwajalein Atoll is another small, very small island in the Pacific that is basically everything is corroding. All of the infrastructure is corroding there. So we've been tasked with trying to figure out how can we help Kwajalein with their corrosion. And that's all I got for you guys. So the next slide is just me saying thank you for listening to me ramble. And if you have any questions, cool. If not, I know we're behind time, but I do know that Jim's going to send you guys my email. So if you're interested in chatting more, feel free. Thanks, guys.
Thank you.
I just have a question. Can I read it? Go ahead. I think I saw in one of your slides, I think probably the second or third, that one of the areas for research was on the embedded sensors. So is that right? So are you embedding sensors for in the paints, or how does that work?
Can you repeat your question? Because I couldn't really hear it.
Oh, okay. I don't know. Well, if not, that's fine. I can just touch base later.
We should get into feedback from the other round.
Yeah. Already. Oh,
Yeah, it's mixing in with your questions. So.
no worries. No worries. Okay. Okay, yeah.
Callie, I'm sorry, we got another conference room right up next to us in the, they're pretty loud and it's mixing in with the questions, so.
Okay, no worries. I'd be happy to answer it. Jim, shoot them my email.
Yeah,
It's really
sure I
easy.
will.
And I'd be happy to chat more. Thanks, guys.
Sure, Kelly. Thank you.
Kelly, thank you very much for joining us today. And I know that you filled it for Dr. Wilson, but we are grateful that you are here.
I appreciate that. I'm her right-hand girl, so you know what? She trusted me to provide that information. I hope I portrayed it well. Thank you guys so much for having us, and I hope you guys have a great rest of your day. I'm gonna sit in for a little bit longer, but I probably will dip out in a little while.
All right, thank you. So this part of the presentation for the audience is to share with you the capabilities of doing research, especially the topic that we have for the collator at the universities. So I'm going to, Jim gave you the package, and the slides have all the capabilities listed. And I will just pick out maybe few slides from our part, and then Dr. Pedro Cortes is going to come from Youngstown State, share with you some of their capabilities. So research infrastructure, and again, it's in the package. We are a state university, Northeast Ohio, one of the three state universities in the corner. And if we go a little bit, it's east, we find Youngstown State. And Dr. Cortes is going to talk to you about a couple of things that we do, and kind of we have been recently in the news for our report on sustainable polymer systems. And especially covered under State Innovation Hub and DVIDS Hub, along with some of the research that three of my colleagues are going to share. Forward, please.
Thank you, say that.
Yeah. Forward.
We're gonna try to catch up a little bit.
All right, so what we and so the mission that we have along with research is workforce training. And we are very proud to have a linkage of classroom taught knowledge with what students experience in real life. So experiential learning, this is a this is very well integrated in our education program. At undergraduate and of course in graduate program, we also have intensive possibilities. So when students graduate, they know the basics, they also know the real life problems, and they can get into the job market in fair time. So I'm not going to spend much time. It's a College of Engineering and Polymer Science degree programs. We cover an associate degree, undergraduate degree, master's and PhD in several disciplines. So you will have that package. You can go to the next one. So the focus areas of research, I know that we are doing materials today, especially for harsh conditions. But in College of Engineering and Polymer Science, where other units, academic units, chemistry, physics also interface, are divided into these 8 areas. And in each case, sustainability is a strong element. And advanced materials and manufacturing part would be presented by some of my colleagues today, along with some of the sensors and electronics work. We have polymer science and polymer engineering. That is that's what the universal acronym is. I mean, as soon as you meet someone, they would say, "Well, you guys are good in polymers," but it's a comprehensive university, research university, so we integrate a lot of other disciplines in it. So it's 8 focused areas that we are currently working on. Okay, so the first one that I would like to share with you, and we are very happy and proud of, is the Center for Precision Manufacturing. There was some discussion on additive manufacturing and advanced manufacturing. Now, this is subtractive manufacturing, but on a length scale that is not routinely done at university research. And so I would like the attendees to keep track of, and keep in focus that this is a skill that we are building. So we can go to the next one so that I can elaborate a little bit. So this is a new facility named after Timken Foundation Center on Precision Manufacturing. It's a new space that we're just building, and it will have about $5 million worth of equipment. And research would be based on an industrial consortium type of model where members are going to decide what kind of projects should be worked on by the faculty members and graduate students. And then based on that, the funding would be given. So go forward, please. So some of the capabilities, if you look into the bottom chart, length scale in millimeters, we cover, up from 10 nanometers to about 10 millimeter type of manufacturing. under one roof. And these are some of the capabilities that we have: fabrication, machining, grinding, super finishing, and even focused iron beam milling. And these are some of the equipment that we are building. Okay. And these are the pictures of some of the machines that are there or will be there in that new facility. And again, what I pointed out, that the length scale that we are addressing in this precision manufacturing center is not usually done on a university research lab. So smart factory emulation. So we will have modeling work done where data sciences, AI, and ML are all integrated, and to guide some of the precision manufacturing processes. And then we take some of those knowledges back to classroom and teach our students, because if the length scale that we are offering in these kinds of manufacturing processes, these are not usually practiced in industry, then our students would create those kinds of industries of their own. And so that workforce training program goes hand in hand for new type of knowledge that we create in our laboratories. This is another one, especially it's a tribology lab. So we hired Dr. Chris Delacourt from NASA Glenn Research Center. He's world-renowned expert on tribology. And especially I want your attention to this extreme environment bearing tester. Now, this is something that is not routinely done in university laboratories. We have that capability. And this slide is with you, and also the hyperlink is there to go and access the website. And so the purpose of me coming up here is to tell you that colleagues who are going to make presentations on some of the research, we do a lot more, and they are all well integrated. So these are some of the work that we do, and the market charts are with you. Please feel free to read. We need to catch up with time, but I will highlight some of the ones that I really like you to find, even go forward. Okay, so CAMP is another center directed by our good colleague Katie Tan. This was funded by Department of Defense to study corrosion of materials and to prevent corrosion of materials. So we have a lot of instruments in our laboratories to do the testing. So we are kind of, as research problems have changed, we are using those same kinds of instruments for studying materials performance. And now, when this was founded back in 2010, I believe, at that time there was no analog effort from the modeling side, and now we are basically bringing them together, and we study materials performance. These are some of the equipment that we have. And this also goes, in tandem with the Center for Precision Manufacturing, where we manufacture and then study the material performance. Okay, it's a list of equipment that we have, and I'm happy to leave those slides with you. Go forward, please. So CARES, I know my good colleague, Dr. Ilma Sozer, is going to talk a little bit more about it. This is on advanced vehicles and energy systems. So he has a couple of projects on that. So hopefully we'll listen to him a little later. Go forward. These are some of the projects that we are running in those labs. Go forward, please. Okay. So the polymer part, my good colleague James Regan is here. He's going to talk about sustainable polymer systems part. But University of Akron, as I pointed out, this is one of the eminent centers for polymer science and polymer engineering research in the world. We have a very strong program, graduate program. We launched our undergraduate program 3 years ago. And we are now thinking of launching another 2-year program so that we can have instrumentation specialists trained at our facility, so that would be coming forward. And this, all of these are done in a, well, most of the research equipment for manufacturing scale research equipment that you would not find in academic laboratories are located in the National Polymer Innovation Center, and one of them is this cast film co-extrusion line. It's a semi-commercial scale. And I invite industry colleagues to take a look at it. There is a website you can also take a look at. So here we are able to combine 3 polymer systems in a layer technology to get about 128 layers confined in probably 50 to 100 micrometer thin sheets. Okay. So one may be corrosion inhibitor, one may be barrier resistance, one may be giving you some kind of refractive index that you need. So feel free to try that. Go forward, please. And then another one is electromagnetic processing line, and this is where if you want to have multiple functionality on a polymeric substrate, for example, electrical conductivity only in the thickness direction, but complete insulator in machine direction, this is a way to go. If we have magnetic line, and also we have electrical line for field alignment of filler materials while we are processing or making a sheet of material from a known host. Again, this is semi-commercial. You are welcome to come and use it for of course for a fee. So solution casting line is another one. You see 32 electrospinning stations where you want to electrospin a material system on a film where the electrospun fibers would be embedded to give mechanical strength, or you can carbonize it later to get certain electrical conductivity, or you can also have some magnetic particles embedded in it, and that would give you certain multi-functionality. While you do not sacrifice the production rate, it's again, it's semi-commercial. Biohybrid coating line, this is for people who are interested in, and it's almost like, in a controlled environment. If you want to have tissue engineering scaffold, if you want to fabricate scaffold for tissue engineering, drug delivery, and during the opioid crisis, this became the workhorse of making material systems that would, deliver the opioid drug without intoxicating people. And this is something that people do. So we have those tools. Electrical injection molder. Now, this is like the conventional processing that we do in conjunction with something which is for precision. Now, in injection molding, for people who are familiar with that, from part to part, there would be a variation of weight. So with these kinds of machines, where you deliver precise amount of polymers to your injection molded article, that part to part variation is minimized. Okay. And we have that capability. Then we have, Kelly talked about curing, coatings, etc. So we have that capability here. Go forward. All right. So that's all I want to share with you. There is a lot more. Please feel free to visit our website or drop me a line, and I will schedule a visit at University of Akron, and we will serve as a good host to have a dialogue with you and how we can work together. So let me invite Pedro Cortez talk about Woolstown's capability.
Thanks a lot, everyone. We're going to share it for this information. It's available today, some of the tricks are in the chemical engineering and actual science department. And giving my colleague also comes for. I just want to give a kind of perspective of the capability that we have at Johnson State University. We are probably about 40 minutes from Akron. We are in the northeast of Ohio, we are just pretty much in the backyard of American Mix, right, which is the National Additive Manufacturing Innovation Institute. Obviously, as an academic institution, we do from metal organic frameworks, batteries, lasers. But right now for this talk, I'm gonna try to concentrate on what is pretty much the additive manufacturing that is what I'm seeing of more interest right now. And we can move to the next slide. We have all these 7 technologies to Johnson, from the batch stabilization, chip lamination, and so on. I'm going to try to concentrate on the 3 or 4, which I believe will be of more interest into what is called high performance materials and storage. Next one, please. One is the binder jetting. Pretty much is the powder is spread out to be a metal, to be a ceramic, and you use kind of like a glue, the binder. It kind of fixes the structure, new fresh material goes on the top, and this kind of repeats over and over. This is kind of a layer to layer process. We have the S-Max, which is a really kind of largest printer. It's for silica sand, so you can create molds for casting. And the nice thing is on the casting is well taken by the industry. The only thing that you are changing is how you are making more, right? More complex structure. But we have another system, the Enflex InnoveNex1, which are just more, just smaller systems for R&D. So we have been able to go for copper, stainless steels, ceramics, zirconia, carbides, name it. So anything that you can have in powders. The nice thing is that we can explore the different kind of looser binders. So we can have a solid structure that often needs to have some symmetry. So now it's in a really solid state, and probably also you are going to have some real porosity. So we need to carry out some infiltration so we can have a really high density. So these machines are open. We are definitely from this kind of collaboration. Yeah, next one. Laser powder bed fusion. I'm not going to spend a lot of time on this because that's a lot of institutions have this kind of systems. We have the Pro XG20. The EOS belongs to American X, but we have a chance to do them. These 2 machines can use reactive materials because they are in a well-enclosed system. And we just have 2 new exact printers. They are really small, right? Which is kind of convenience for R&D. Those are non-reactives, but it's very easy just to change materials from Inconel to stainless steel and so on. We are doing obviously a lot of kind of crazy R&D. So some metals coated with some ceramics. That's what we do as in the academia, right? Our TRL level pretty much is between 1 to 4. Next slide, please. One thing that is really nice that I'd like to bring the attention here is in the bathtub ionization, but especially in DLP, because we have been able to push a lot into the ceramics and metal. And I'm not talking about the Form Lab, but I'm talking the Armaflex that you can go 20, 30 micron resolutions, and the Boston microfabrication that you can go into the 5, 10 micron resolution. So there is a lot of opportunities for electromagnetism, microelectronics, board packing, power lines, and we can do single materials, multi materials, lattices, and so on. Also, we have been able to do all the carbides that are important for electronics or high temperature applications. Our systems can go, in the case of the Armaflex, up to maybe 4 inches by 4 inches by 4 inches in that range. So still we can produce you can see here, those one that later it has kind of a millet and allow it when we put some metal, and that's what is for some power electronics. But at the end of the day, it's an open source. So we can have the resins, the metals of the ceramics, and we can print a part with a really high density. Next one. Direct energy deposition, we are kind of proud of that. We have the powder direct energy deposition. So powder comes and the laser goes and pretty much solidifies that powder coming to the bed. We have it in a 5-axis. The system has 4 hoppers, so that means that we can change powders and on the fly. You have an argon shield, so we can go for
some interesting material made in titanium. We have a new one, which is a MESA system. This does not use powder, it uses a wire. For me, I like more having a wire because you remove all the presence to having powder, right? The handling is way easier with wire, and you can have even an aluminum wire, and it's very easy to work with it instead of having aluminum powder kind of explosive and all the paperwork. We have been doing a lot of work now for repairing. This is a project being funded by MetaMex and the Department of Defense through the Air Force. Here, for instance, on the right-hand side, this is just an insert that we just printed. Inside there is a cooling channel, right? So it's an insert for an injection molding, so you can bring down actually the time of production. This is also 5-axis, and we call it hybrid. Why hybrid? Because you do additive, but also you do subtracting at the same time, right? So you start having wire, you have all the printing, you switch from the CNC, it does all the subtracting, and you can just go into this interwoven process. Next one, please. Additional 3D system that we have in YBI, just continuous incubator, we have access to the XJ, high resolution, high density ceramics. It's more kind of limited in the materials, zirconia and alumina, but the definition is great. So, and especially for now, all the microelectronics that is happening in Ohio, this could be definitely an answer. We have a salt jetting, 20 micron resolution, 2 photon polymerization. This is really a very low tier level 0 to 1, where we're trying to identify interfaces, interactions, and so on. But well, it's available for any kind of collaboration. And another bunch of systems, Portus and 50 from labs and AFRL, and I can keep going and going. Next one, please. So yes, I there obviously some kind of pictures, schematic pictures. It's multi-dimensional. We have different kind of characterization infrastructure, atomic for microscopes, DSC, TGS, and I can give you really a long list. What I think is at least for what I understood would be something for materials under extreme conditions. I believe this could be an interesting capability. We have an actual ballistic range. We are using right now armor piercing 308, but we can. It has been designed for a 50 cal. We have the tick machine, 20 hertz. We can go for minus 130 centigrades to 1400 centigrades. We have also that gun, 1-inch barrel, so you can even put a simple kind of frozen cookie Oreo to a steel ball, name it, right? That can go to 1,000 meters per second. We have all the high-speed video cameras. We have a lot of furnaces. We have the TEF that can go to 2600 degrees Celsius. That is vacuum and inert environment, full instrumented impact tower. So in terms of the dynamic testing, I think we can go from a simple speed Hopkins from bar expression in materials of the high conditions to really a ballistic range. So it's a big, really a big rainbow that we can offer in dynamic testing. The next one, please. Also, X-ray, XRD, XRF, and afflection, FID, where we have 4 or 5 different kind of SCMs, EEMs, hardening and non-indentation, CT scan systems, and also we have MTS, Instron, compression, flexible, like obviously, but you can find that also in many other institutions, but also we have that kind of basic infrastructure. Last one, please. No, I think there are 2 more. Kind of quickly corrosion testing also, like we have in Electrobike and T4 also, we can do something with salt, with sulfuric or low kind of pH systems. It's Dr. Polymartin has that kind of infrastructure available. Next one, please. So hopefully I'm not taking too long. Just 1-2 more minutes. We just received a call to the airport to create some kind of assurance and microelectronics project, and we really do a nice lab in terms of the acquisition of electronics. So Bansi, you can just spend a couple of seconds explain.
Yes, so we do have an fertilizer. We are able to print like 3D antennas, as Dr. Cordes mentioned, so we are working with BMF.
5 micrometer and also a resolve printer, so we can be flexible. Also, a terahertz antenna, so we're able to use some of the machine. And also we have power device and lighter, which can go up to picoamps to 1500 amps and also 10 kilo volts as well for testing for IBCD characteristics. And also obviously you can see signal analyzers and program. Yeah, next slide, please. I think, in addition to that, as Dr. Cordes mentioned, we have that Advantage grant, part of that microelectronics grant from Air Force, and we were able to get like harsh environment power. Design using TSMC 28 nanometer and also EAD software such as Cadence Virtuoso and Synopsys IC2, and also for designing antennas using ANSYS. So we have some good publications lined up and from these softwares.
All right, yeah, really nice data acquisition system. So the last slide, I believe, which should be next one, is our new Excellence Training Center. We were pretty much established there by our previous president, Jim Trexel, right? Everyone knows. Very quickly, it's offering a lot of training. We are bringing industries, we are bringing community colleges, high schools, we are providing certificates. Jackie Ruler, who's the director, is doing an amazing job. We also have established data with YSU Foundry. We can use pretty much gas, ferrous, non-ferrous system. It's completely automated. And I think with that, pretty much, I hope it didn't take too long, but I can just give you a kind of high-level overview picture of the things that we have at Youngstown, low tier level, just happen to have any collaboration. So thanks for our question.
Thank you.
Okay, Nick.
All right.
Thank you very much. I'm Greg Morcher, mechanical engineering at Akron. And I'll go through a few slides with my collaborators here, especially stuff aimed at materials or modeling of extreme environments for various applications. Next slide. So this is really an overview of my group. I come from NASA Glenn. I was there for about 20 years prior to joining Akron in 2009, and I worked on straight-up craters and composites, especially for hot section, jet engine, and hypersonic applications. And so really, there I worked on material development more, but since joining the university, it's been much more aimed at understanding properties, various kinds of extreme conditions, health monitoring, NDE, life models, these sorts of things, working with a lot of government and OEMs over the years. You can see we have quite a bit when it comes to understanding materials. We use up at all kinds of temperatures, we use acoustic emission, electric resistance, DIC in order to monitor damage regression and try to help with failure models and this sort of thing. We've worked on all kinds of different actual properties, off-axis properties, many different high temperature exposures, either through furnaces or through a burner rig system we have talked about in the next slide. But we do modeling with Alex Babitsky of CVI-SIG infiltration, so the fluid dynamics guy, and he's been doing some modeling of that for some of the CMC systems in the silicon carbide world. And then we use electric resistance as a health monitoring technique. And Alfred Holdem has been monitoring that, especially for the silicon containing melt infiltration systems. So we've been developing some of those models as well. Go to the next slide. So this is probably the coolest thing we've got in our lab. This is a burner rig. It is a HVO flame, high velocity oxygen fuel. We got a couple different nozzles. We can go from about 200 meters per second up to over 1,700 meters per second, but over Mach, we get exceed Mach 5. We can go up to about 2,000 C, from about 800 C to 2,000 C. So we have that whole range. So really, this is geared at, again, sub to super to hypersonic part, hot section components. We can look at, it's also a particle ingester, so we can do particle erosion, molten particle erosion, sea mass, ingesting sand, those sorts of things. We've done a lot of different aspects. We have this, there's an NTS, a horizontal NTS that is here in the rig, so we can do uniaxial tension. We do a lot of code systems with that, both TVC metal systems as well as EDC CNC systems. We can also do a flexure. We built a flexure rig, which isn't shown here, to do morphing structures. So there's a lot of interest in being able to do morphing structures. We can do that up to Mach 5 and 2000 C as well. We can vary the water content somewhat by the gas composition. So we get up to about 10% water vapor. It's not like a real engine, but it's better than just a regular air test or something like that. And again, we have quite a bit of diagnostic capability. We have clear cameras on the front and back. We have a pyrometer. We can do electroresistance in situ to monitor the health monitoring during the test. And so this kind of gives you an idea. This is a 1700 C front face. Back face is about 1500 C. So it's a 200 C thermal gradient. We got thermal gradients through the thickness. We got thermal gradients the axial direction. And we work a lot with modelers to try to understand material behavior and response with respect to the various conditions as well as the damage that is incurred. Next slide. So my colleague, Chris Daniels, who is also from NASA and still works directly with NASA. He has some people that are physically there as contractors. They work more on the seals group. So here again, high temperature seals. So they have various ceramic and metal type seals for various applications. And they're very much interested in designing these and testing them under very extreme environments. They have they're developing a high temperature test rig at NASA. They have various tribological capabilities as well for some of these different materials to understand how things work when they are rubbed up against one another, various metal and ceramic systems. And they have these other high temperature speed load devices and gaskets. I'm not as familiar with that, but he's got Chris's email there. So if you're interested in this sort of research, please reach out to him. Next slide. So Al Babitsky does, he's a modeler mostly, so he's a fluid dynamics guy. So he does a lot with, ablation and various other kinds of super and hypersonic flow. And so this is an example of his supersonic flow for air fluid or various angle of ramp surface. I believe it was in the hypersonic range as well with this, but this was in conjunction with the Air Force. And they were modeling some of the flow characteristics for some of these structures that were done experimentally. And his model is shown over here. I think these points go with this line, these points go with that line. So he's able to do some of the modeling for these sorts of systems. Go to the next slide. And here's the case of ablation. So he's done quite a bit of work with ablatives and under various conditions. And I believe the big thing about this was there was actually a defect in the structure. So it was modeling ablation around a defect of, I believe, a carbon-based ablative material. And you can't even see the defect, but it's in there somewhere. And it shows that he was able to model that pretty good. Again, his email is there if you're interested in this sort of stuff. Next slide, please. And then we also do quite a bit with AM metals as well. This is just one example of some stuff that Professor Kanan is doing. In this case, they were actually making additive manufactured metals and then going through various grinding steps in order to, put residual compressive stress in the surface, change the surface of the material to try and improve fatigue resistance properties. And so there's a couple different air and liquid-based techniques that they were modeling in order to get some improvement in the surface conditions or to improve fatigue life properties, which will show a little bit down there. Again, if you have more questions about this, that's going to seek out Professor Kanan. I think that's it, right? Yes, sir. All right. Any questions? Next.
So I need to deal muscles. So I'll be presenting some of our research, our department.
Can you speak up just a little bit? We got the noise outside there, it's kind of not helping you at all, so.
Yeah, within our called Center for Advanced Legal Science and System Laboratory. So we have been working on the transportation electrification, energy systems, the renewable energy, and hopefully the systems applications to the transportations and the aviation applications. So we have several grants from the federal institutions, state, and we have a good collaboration with the industry. Thanks. So the energy systems and transportations, the growing concern is the environmental awareness, energy security, developing efficient systems in the for energy conversion devices, critical elements of the power density, acoustic motor, electromagnetic reductions. So what are the tools that we have prepared to address these concerns? Definitely critical element for us is the advancements in material and device technology. So I will have slides to so what type of materials, new materials that we could use to address this concern, and the device technologies, both like the electric machines and energy conversion devices and the power conversion system. So of course the new architectures and the topologies. So the new development in the material science, new materials enables us to use our new topologies that we couldn't use before to address the problems. Advanced control and optimization techniques, especially the machine learning techniques and AI implementation, enable us to use new controls, new sensor implementations. And also the electronics developments, the electronic sides, so the fast computers, fast embedded control systems provide us to use the high performance simulations and implementations on the embedded control. So I can go to the next slide. So I'll start with the electric machines. It's very important, especially transportation electrification. Electric machine is a key part for the traction, and for the aviation, for the electrification aviation. The propulsion is also the key part is the electric machines. What do we want? Like depending on the applications, we want either the high power density, gravimetric power density, or high volumetric power density. Definitely high efficiency. So we don't want to use all the power in the conversion systems, because it's really an energy is the asset for the transportation and the aviation. Efficiency, the power density are key, and the cost. So the several machine types, the induction machine, sequence lattice machine, interferomagnetic machine. So if you don't want to use the regular material, the switch lattice machines, the induction machines, are important. And then new algorithms, new topology, the axial flux magnetic machine that allows us to use a higher power density to get a higher power density. So the critical part for the electric machines are the laminations, ferromagnetic materials for the current magnetic machine, and the magnets. In addition, the wires that we insert in the stator or in the rotor in some motor applications are critical. So the cost, the efficiency are based on what type of materials that we use, and then how we optimize the machines for better performance. The windings is one example. So either with the standard winding, new techniques are the hairpin winding. Between them, the field factor, although we have a slot area here, the amount of wire that we could put is like, you can only keep in the 50%. With hairpin winding, you can improve that, like 70% or so. Definitely, there is an opportunity here to improve the slot queuing. The additive manufacturing is something that we are looking to improve the field factor. So why is it important? It's directly impacting the efficiency and losses. So if we improve the efficiency here, we can reduce the thermal requirements. We can improve the efficiency, reduce the losses. So this is like how we can implement the hairpin winding for the. This is really a kind of enabling technology in the transportation for developing an intercom application. Next. A bit more on the material side. The key part is the ferromagnetic material that you mentioned. It is how we can improve the saturation flux, the lead point, and then we can improve the get the high flux density for the electric machines. For the magnet, how we can improve the region here so that we can go for the higher flux density for the magnet, and then extend to the higher amps per amp for the higher amp, so that the material does not get demagnetized. So the key part also is important for the thermal performance. So several cooling techniques that we have been implementing to improve the cooling thermal performance of the machines. Another material improvement that we have been looking is the micro wires for the electric machines. So one example is the thinkless darkness machine, where we have the saliency. The key part that is kind of not enabling us to use it for the mass production for the synchronous darkness machine is the amount of saliency that we get is limited, and it's also the mechanical performance and the high latency is kind of contradicting. However, using the micro wires, the thickness is like 20 micron, so we can improve the mechanical integrity of the machine as well as reduce the core losses significantly. This is pretty much reducing the core losses. That otherwise we would have a high core loss with the combinations. And what next? So one kind of project applications is the development of the front-end motor generator for Class 8 hybrid truck. This is starting from the design process of the machines and drives and implementation to the vehicle. Pretty much done. The DOE funding and then the company and university collaborations. So here is an example of the different machine types in terms of ferromagnetic machines, darkness machine, and axial flux machine. Machine learning is implemented for the AI, implementing for the design process, where you could see lots of design options is searching, and then this is like a Pareto front that the total weight over the average load or the corporate load or the current density. So that through the machine learning process, we go to the integration of various parameters that we could select in the machine design and then find the optimum design. So overall, we selected the stage darkness machine technology selected. Not only the efficiency is like lacking, but however the reason that the selection for this machine is like a fault reliability at the when there is a fault in the system. Next slide. It is built and tested in our university, and then developed for the installations of for the track. Another part is the key in the transportation application is the motor drives, the power electronic system that takes the power from the battery and then provides the AC output for the processing driving to the electric machines. Here, neighborhood technology is a silicon carbide type the devices, improves the efficiency, bring the efficiency to 98%, reduce the volume of the overall power converter at 40%, compared to the silicon devices. So you can go to next slide. The dual cluster is another project, the development of the switch machine for heavy duty vehicles. The starting from the design, the thermal analysis, thermal performance, the overall build process, the installations of the windings to this structure, and the testing. So it's all kind of with the collaboration with the local vendors, it's all done at the university. This is our dynamometer facility, 150 kilowatt, 1000 RPM, fully operational, fully like commercial dynamometer, the facility that we have. We are using it for the testing of the developed energy conversion systems, but it's also open to the industry for their testing needs. This is another project I mentioned about carbide devices for the high performance, high efficiency systems. This is a new project funded by Ohio Federal Research Network. Specific application and then federal partner is Air Force Research Laboratory. It's a development of the high bandwidth, lightweight, modular, blind unified phase interactive DC emulator. This is really for when we develop your system, you need to go and test it in the actual applications. However, most of the time that either the truck is not ready, the airplane is not ready, or testing. So this system is basically developing an emulator that emulates exactly like electrical system, so that any unit is developed can bring here and test it. So the rest of the system is gonna mimic pretty much the electric system of the airplane. So the kind of part of this project is to the traction development for the structure generator, development for the drone application. That will be another outcome for the project. The high monitoring of power lines and the DC transit systems, another area that we have been looking, basically determining the aging conditions, like aging of the electric transportations for the DC transits, and also the transport for the electrical transmission and distribution. The idea is started with like looking at the high frequency behavior of the line. That is directly linked to the age, the performance, high conditions of the power lines. The system is pretty much injecting the high frequency signal into the line. So look at the high frequency impedance and correlate to the performance of the system. However, as you know, like the electrical system is all connected, all grid is connected. So if we are measuring the conditions, we are pretty much measuring the whole grid in the United States. So we actually implemented the blockers so that we are only looking at a certain region, certain section of the line. So that's successfully implemented on the power lines. The current project is the Department of Transportation for the DC transit systems. Similarly, we do application. Now looking at the segmented line, then with its performance. Another application that we looked and that we have developed is the non-electrified structures. So like power towers, for example. So we look at the high frequency impedance behavior and correlate its performance. So this is our facility in for like testing the power lines, and look at the heating conditions. Again, is machine learning AI is implemented on that. Next slide. Sorry. Next slide. Okay.
Let's go trade.
So Dr. Hart, Dr. Carina Hart has been using developing a directed characterization laboratory. So we have a facility to look at implement destructive testing and non-destructive testing, look at the high voltage and the dielectric behavior of the power lines, and LCR meter dielectric constant and dielectric loss measurements, electrostatic voltmeter space charge measurements, in conjunction with the up to 10 kV pulse generators applied on the systems to determine the partial discharge for either the power lines. And she's implementing the software for planetary analysis, the kind of the tests here through the planetary analysis for the control physics. Next one. And then same tests with the extreme conditions, but under low pressure, thermal shock, humidity, the high temperature, base temperature, and then different the humidity and salt applied conditions. The similar test the capabilities there. And after doing this, similar partial discharge tests are done. And its implementation also linked to the electric machine design, the windings. So I mentioned about the heavy windings, the standard windings, the insulation is around those magnet wires. With the use of the drives, like a high efficiency, continuously applied to the pulse width modulation, is applying a DVIDS for the insulation. It's really harmful for the insulation of materials. So new insulation materials are needed. We're looking at the modeling of the nanocomposites as opposed to organic polymers for coating the wires, and analyzing the effect of the interface on the distribution of the field on the new materials that will be used for the wires coating, and that will outperform the existing insulation materials. So lastly, okay, all right, yeah. Thank you. Questions?
Thank you.
Yeah.
Oh.
Oh, yeah, sure.
Oh, no, sorry, hopefully everybody know that. Hello again. Gonna give just a big overview of the research work that we have been doing, mainly into the additive manufacturing, right? We have been doing definitely working with manufacturing, and if you are interested in having that done on either metal or ceramic, we go into the very basic foundation, shape, particle size. We can do solid particles, foams, multi-layer systems, from carbons to silicon, chromites. We have done also quite a bit into the modeling, right? In the next slide, I'm not going to go into every single detail, but the thing that we just try to understand is what are the relationship of my printing parameters. Let me go to the next slide. The printing parameters towards the actual property and performance of the system. How is your layer thickness affected? How is that particle size? What is the binder separation? So I'm not going to go in every single case, but it's important that you understand that relationship if we want to produce a part that can be mechanically robust. Next slide, please. One of the things that we have been doing is was funded to the Army Research Lab and working with a company called Pipeline. It is we pretty much bring a silica and that is being transformed with a metal and produce something called interpenetrated composites. That's the main equation. Whether it's more in details of that, but you can change the metals. So the silica pretty much is kind of disappearing or it cannot be diffused, but it uses a high performance ceramics. This is great for impact. We have been doing it for ballistics, for heat dissipation, for wear, right? So the beauty of this is that you can actually bring a complex structure and do the transformation, and you will have a high performance metal ceramic composite. Next one, please. There is also a lot of needs for this high performance system, what's called ceramics. It's a bit different. Then you have two phases, not interpenetrated. We can bring again this bromide, this carbon, and we can actually go with this infiltration, and also we have done it with the transformation. We have also been doing a lot into this silicon carbon because it required for the exports. We have a great collaboration with them, with the ceramic directorate. We really want to push a little bit onto the high temperature materials. Next one, please. In the batch polymerization, what we have been doing is also we are using the silica, but instead of using the binder gases, we use the batch polymerization. So this is rather a kind of UV source or laser source, and the ceramic or the silica is kind of suspended on your resin, and you already have some kind of a schematic figure there, some very simple parts. Completely silica, then you do again the transformation into these interpenetrated composites. And we have already done very simple pupils, but also we have done kind of like a lattice structures. This lattice structure is kind of especially graded, right? Because we have different kind of masses or density depending where you're located in the height. And once you have that, we have carried out a kind of we have done a casting. So now you have in one part really hard material, and on the other part you have a metal. So you have a ceramic and a metal, and it's especially graded. And we do run these for the Navy, funded by them, for ballistic applications. There you are, the ammo piercing 306. This is on the kind of lab would say, well, why are you using this? Well, 3D printing is giving you this really nice lattice, especially graded structure. But you can also do a list of casting. This one is completely square, but you can do something that has proportion, different kind of shapes. So when you give it heat, it actually can create another part, another direction. So you pretty much bring down that impact energy. So that is more into the ITR level. Next one, please. One thing that also the Department of Defense is, at least the Air Force is interested, it is in composite tooling, right? So we partnered with them. We have been doing actually tooling based on ceramics. Instead of using the in-bar, they are using kind of low coefficient or thermal expansion ceramics for producing this composite. Actually, this is a right path. So this was pretty much treated in this test max, this zircon, zirconia, and it has to be done in different parts, right? So you see a single structure, but no, actually there were different parts, and then it was joined like a Lego. So you can have it for a structure. Why not printed in a single shot? Because it's too heavy and you can damage the machine. That is actually again something. Different along analysis try to investigate different systems or ceramics that can have a very low coefficient thermal expansion. And that's important. Go to the next slide, please. It is important to have low coefficient thermal expansion because the carbon fiber for epoxy that I've been using in drones and things like that, you don't want to have any deformation, right? So that's why important to have this low CP. For the power, diagonal deposition, and then we have been just printing a section where in the back plate is just a kind of cheap steel or non-expensive steel, but in the cladding, there is a transition from steel to in-part 36. In-part 36 is again a low coefficient of thermal expansion, a low is a nickel iron. Or we can actually maybe the position wherever we want of these powders or these metals, so we can control or tailor some properties like, again, the coefficient thermal expansion. This is what we're done in collaboration with the University of Cincinnati. Next one, please. The one that I mentioned before, which was the laser 5-axis, you can see already the laser, well, it's already printing. We have the pupils, they don't look nice at this point, right? Because it's only additive. So hopefully we have over infrared, so we can actually try to have a feedback in where the thermal spots, if there is any deformation. We are working with Oak Ridge National Labs, University of Texas El Paso, Georgia Tech, and so on. But after subtracting, you can see just change goes into the CNC, and you really have a really nice finishing. Here at the part, this is a mold for sewer. We are making the mold for the side mirror of a racing car. So we already printed, we started printing, but also we are going slowly with this tracking. And there, in this part, when it's done, they are going to lay up some carbon fiber for epoxy that is going to be housing the mirror on the side for these racing cars. Next one, please. I have to remember which one is the next. Okay, here for high temperature application. So we have been working with Oak Ridge National Labs to try to embed high temperature sensors into metallic extrusion, right? Actually, during the printing, they stop the actual process. We insert the ceramic has to be high temperature. I know there's a lot going on with thermal shocks and so on, but we have to succeed and continue the actual printing. So the sensor is embedded, and here we are using a tungsten nickel with some moly or some antimony oxide, different kind of junctions. And since they are also high temperature, they can really support well above the 1200 or 1500 degrees Celsius. So the idea is not only measure what is the thermal temperature of your metal structure, what is being built up, but actually in the service. And a different kind of shapes, forms, and here can you click that video? We are actually here. Dr. Van Tibor was using his eye glares and so jetting. Can you go back and click it? If not, that's fine. Just a kind of it's a demo, right? So we can use pastes, but also we can use inks if you have how lower viscosity. And so actually the machine it's an open source. We can change different kind of resins. It varies from the moly, silver. We have been over there mentioned this tungsten nickel. And I say tungsten nickel because tungsten per se by itself is so difficult to work with. You already know material or element with the highest melting point. So the nickel just kind of bring down that melting point. We have been doing also antennas for high temperature applications. And you want to mention okay, next one, please. We have been working, as I mentioned, for this kind of mobile systems. But here the important thing to understand is that interfacial interaction, especially when you're working with different animals, for instance, non-zirconia or metal ceramic. Again, this is for power electronics. And one thing that really we are pushing forward, it is for batteries. So we got a grant to NASA and we try to print batteries in a single shot. My collectors, my anode cathode, and also a solid electrolyte, right? No liquid. We are going there. We are going there. A lot of analysis characterization that we have done in terms of what is your best sintering condition. You are having different animals, right? Different sintering poles, interfaces. What is going to be your running time, your ramp, your cooling ramp? A lot of this kind of very low TRL level, what we are doing. Bunch of materials there. I can give it going of that we are able and we can print. All right. Next one, please. Oh, that's it. All right. That's okay. A big overview. Just something you can find out in a bunch of papers with just an idea of what things that we are doing via additive manufacturing. Thanks, appreciate it. Well, any questions? Sorry. No. Okay, please. You probably might be smaller than I do.
No worries. I guess I'm what's standing between everyone and our friends. So
That's correct.
My name is James Egan. I'm in the School of Polymer Science at the University of Akron, and I'm going to represent some of the polymer breakthroughs in our department. Hopefully, some of the technologies I talk about resonate with some initiative within your own organizations. Please reach out, happy to discuss further and connect you with the primary researchers on this project. So this first project is part of our additive manufacturing of metal composites. Now, what's exciting about this is that Professor Weinan Zhu, who's leading this project, we're doing fused filament 3D printing of these metal composites. These are low temperature, below 200 degrees Celsius to print these parts. The way that that's achieved is through these liquid metal alloys. So gallium, indium, tin is a metal alloy that has a very low melting point. You can blend it with a polymer and then 3D print it as though it were a polymer for plastic. These are highly thermally and electrically conducting materials. You're probably not going to use them for printing fuselage parts, but for advanced parts that need to be electrically or thermally conducting, these are good options. Next. The other project from the Zhu lab is in heat dissipation composites. And so as the technology that they're really focused on here is for use in electronics. So as electronic devices become more dense in their circuitry, they generate more and more heat. Dissipating that heat rapidly without sacrificing the mechanical properties and the temperature resilience of the material is a challenge. And what their approach has been leveraging are two-dimensional materials, primarily graphene, single layer graphene, but they've also worked with other 2D nanocomposite materials. And their critical breakthrough here is that their materials are very stiff, they're very tough. You haven't sacrificed any of the mechanical properties to achieve this thermal conductivity. Next slide. Now, if we go from high temperature down to our low temperature, Professor Casey Tan in mechanical engineering is looking at multi-layer composites in Arctic applications, where we're talking about minus 70 degrees where they do their testings. Under those conditions, virtually any polymer composite is going to be in a glassy state. It has a completely different fracture and failure mechanism. And so what they're excellent at is performing the lamination and the testing of these materials. They produce what are called sandwich composites. It's a combination of carbon fiber and glass fiber composites. And they've done a lot of work characterizing how these materials fail and delaminate when you go to these extreme cold conditions. And on the next slide is another project from their lab where you're looking at the interface of a composite and a metal. So wherever you have a joint between a titanium and a carbon fiber composite, how does that joint fail? They've developed a lot of finite element analysis for these complex failure mechanisms. They do XRT to characterize those materials, and they've also developed predictive models for these systems combined with their own results, their computational data, and results that are out in the literature in order to develop advanced analytical prediction for these metal composite joint failures. On the next slide is how they actually do this testing. And so it is a unique facility. It's a high-speed camera that monitors these impact tests and these mechanical failures at these extremely low conditions. And so if you ever need tests or mechanical analysis for those kinds of environments, Dr. Tan is an excellent connection for that. Okay, this next project is going to shift now towards coatings and UV radiation. So melanin is what Dr. Gina Jwala is interested in. Melanin is what gives skin some color. It's used in nature to produce all sorts of structural colors. And how it interacts with radiation is poorly understood. And so this is what Dr. Gina Jwala studies. This is a collaboration with the partners you see in the bottom right here and NASA, and they've actually put these samples on the ISS under different configurations and are studying how the UV radiation interacts with these materials. On the next slide, for example, they've made aerogels, silica aerogels that are coated with melanin particles, both synthetic and natural materials. And what you'll see here is that you can see that as it's exposed, it gets darker and darker. Basically, the aerogel's getting a tan, right? And what they've done is they've characterized chemical changes in this material and understood how it can be used as a UV protective film. So for UV protection, this is a natural or a synthetic scalable alternative to many existing materials. On the next slide, the other interesting thing about melanin is that as it's exposed, it actually absorbs more and more radiation. And so it's a self-improving coating is what they found. This discovery was filed as a joint patent between the University of Akron and NASA. And you can find out more by discussing with Dr. Dianjwala, and that's what these results are showing here as well, the absorption power. Another coating is from Professor Mark Socek, and what they are studying are more active coating materials. So can we have a coating that's not only protective, but perhaps generate fuel like hydrogen by combining it with nanocomposites with zeolites, absorb radiation, produce hydrogen gas, or friction and heat through hydroelectric effects in order to generate electricity or be actively involved in the spacecraft. As was mentioned earlier, the facilities at the University of Akron allow us to take these to pilot scale production for these coatings. And so we have a solution casting line, a semi-continuous process, as well as a cure line for coatings, whether it's a UV or an ion cure coating. And then the last project I'll share with you is from my group. My group's interested primarily in sustainability of our polymeric materials. And what I'm showing you here are some of our projects focused on how do we use carbon dioxide to make polymers. I think this is a really interesting approach, not only from the sustainability aspect, carbon footprint sustainability, but even as a security standpoint. It's a resource that doesn't follow any boundaries, right? It's in the atmosphere. There's no other carbon resource that is free flowing around wherever you're deployed. And so what we're trying to do is figure out how to capture and then utilize carbon dioxide to make polymeric materials. Some of the materials that we synthesize are advanced photonics from bottle brush polymers. And so we make bottle brushes that are 40% carbon dioxide. And we studied their mechanical properties and their applications as coatings. And then the other material that we've developed is for epoxies. So wherever there's an epoxy resin, we have some exciting technologies that are CO2 based. And so they are lower cost, projected to be lower cost once they're scaled at least, but they're also recyclable. And so some of our materials, what I'm showing here is a carbon fiber panel that when you treat it with a specific solution, you're able to recover the fibers and reuse those. So if you have large scrap rates, this could potentially be really useful for repurposing a thermoset. And our mechanical performances are comparable to traditional epoxy. So this is a collaboration with the DOE and Raytheon. So I think that's what I have. And thank you all for listening.
Yeah, you want closing remarks or?
No, I was gonna say, thank you all for sticking with us. I learned a lot and I work with them. So I hope you can join us over at
Dayton Beer Company.
Dayton Beer Company. So we've got some
Just straight-
snacks there.
Right across the parking lot, it's a black building.
Oh, we can walk to it?
Yeah.
Okay,
You need our person.
Yes, sir.
okay. So snacks are on us. University doesn't let us buy beer, sorry.
The Air Force Association does, though.
Oh.
They're there.
He's got that.
Okay. Yeah.
Never mind.
Except for.
The concept would Oh. Of course, yeah. Thank you very much. Thank you very much.
And I think you guys.